All right, everyone, let's get started. I think we're a couple minutes behind here and just working out some issues in the background. Welcome to day 2 of the HPC Partner Bootcamp. Really excited to be able to obviously put this on and hope you enjoy. We've got some wonderful content that for us to go through today. So I want to welcome everybody. This again is our second annual HPC plus AI Partner Bootcamp. We are virtual, but we are live. So I want to make sure that everybody is aware that we've got some great presenters coming up today. They will be speaking live, and we'll cover it in a minute. But we do have the ability to do some live Q&A through chat. Once again, I am Mark Eastman. I'll be your host for the next couple days. We've got this session and tomorrow left. I'm part of the worldwide HPC Global Black Belt organization, so really happy to be able to kind of host this event. So far it's just gone really well. Hope you guys are enjoying it as much as we are, providing all this wonderful information to you. Let's take a quick look, again, re-review, today's agenda. I think I'm a little bit off. I know Asia folks are coming in this morning on the 25th, so just recognize we're in day 2. As I alluded to yesterday, it's really about the products. We're going to talk a lot about the infrastructure we feel is industry leading. We're going to talk a lot about our compute hardware. We'll talk a little bit about storage and the different storage applications that are available, and as well as some of the software platforms and some of the efforts that we are putting together, the tools that just kind of help bring all this together. And Rob Fruchik will do a really great job of kind of putting a bow on all that. Yesterday, we did get some feedback. It said, what is it that you guys offer that is so unique to HPC and maybe a differentiator compared to, the other cloud platforms out there? Well, I sure hope this through this session, this first part of the session, I'll walk away with some really good answers to those questions. So if you're not getting them, please obviously put them in the chat. We're going to take a break, and then we're going to come back, and Cormac Garvey is going to give us a really good session on how to tune all this. Once you get all the infrastructure kind of in place, there are tricks of the trade and all sorts of different ways that we can, kind of improve the overall performance, based on specific applications, specific solvers, whatever that may be. And then we'll finish out today with a partner showcase. We provided our friends from NVIDIA, and they've just got a fantastic presentation. Before I jump to some of the other logistics, I just want to make sure, again, I remind everybody, you do need to register for each day individually. So if you haven't registered for day 3 tomorrow, please do so at the link that we've provided here. If we look at a little bit of what we're trying to cover, again, we want to have a Q&A and try to provide some feedback. With limitations of the system, we can't do that using voice and live. So what we can do is respond live to Q&A chat panel. And if you look at the kind of the top right-hand corner of your team screen, you'll see some bubbles, and basically if you highlight over them, it'll say chat. Go ahead and submit your questions in there. We've got moderators and folks coming in and basically starting to answer those questions. Don't be surprised if someone chimes in and said, hey, it would just be easier to kind of take this discussion offline. Here's my email. Send me an email. So if I remember right, last night, this was a very good group in terms of asking lots of questions, and hopefully we gave all the answers to those questions. The other 2 items I do want to highlight is that we will have these sessions on demand. So if you happen to miss one or want to re-review one, there was a link provided in your registration email. You can go there. And then let's say approximately 72 hours, you should be able to view some of these sessions on demand. In addition, we do have the presentations that will be available. There's another link where you can go to that we're highlighting here called /deck/HPC that provides presentations. And again, you can have access to those if you miss something or wanted to re-review. And last but certainly not least, if any inquiries, any questions, anything's going on, please feel free to email us at hpcpartnerevents@microsoft.com. And as we go through this, I'll kind of help remind folks as we play this out. So with no further ado, I am going to pass it over to Jack Cabot and Evan Burness. They're going to give you a fantastic overview of where we're really strategically headed in terms of compute and a lot of the platforms that are either on our current offering list, as well as some little bit of insight to where we're headed. So Jack, you want to take it away?
Yes, thank you, Mark. Hopefully you're able to start seeing my projection. Can you confirm it's coming through?
We can see it just fine. Thanks, Jack.
All right, thank you, Mark. So quick introduction. My name is Jack Cabot. I'm the lead program manager in HPC Ai Azure Compute Platform. It's a really long term, but what that really means is I work with my team in terms of creating the Azure VM SKUs that are underpinning of the HPC AI Azure VM families, or more easily the H and N SKUs that you see in the portal as part of that engagement. Just a little bit about myself. I've been at Microsoft for over a decade, and it still feels strange saying that. I've had the privilege of working the last 4.5 years with the HPC AI team, building the right team, and really engaging to bring this platforms you see coming to you now through that timeline, because it does take us that much time in terms of looking at planning in the future to really create the platform of the future. So that's a little bit about myself. I'm very happy to be here and share our progress with you. Evan, you want to take a quick introduction yourself?
Sure. So hello, everyone. My name is Evan Burness, and I work on Jack's team in Microsoft Azure. I'm Microsoft's program management lead for the H-series programs, which are our CPU-based offerings for high-performance computing, and I'll be joining Jack during the presentation today.
All right, so hopefully you all had a chance to see kind of the sessions in continuum and start off with the keynotes and the sessions from yesterday. So you'll probably see me do the keynote and talk about some of the high-level direction and strategies of how we think about HPC and some of our offerings altogether. So looking at that purely now from the Azure hardware platform perspective, here are some of the core themes that drive our decisions and how we think of what we're going to invest in, build, and come as products in this space. So not surprisingly, one of the first things we have is basically around purpose-built hardware. And you hear a lot about this, but this is kind of where it really starts in terms of ensuring that we have the right solution in the space of the workloads that run behind and on these systems. And these are high performance where you can't compromise any of the capabilities that customers have on premise. These are the things where customer cost is top and center of mind as part of the solutions. And this is kind of where our strategy has been really to focus on how do we take the best of technologies out there on premise or elsewhere and build that into our offerings. Second is fast and secure networking. And this is, again, a core aspect and not a huge surprise for anybody who's been in the HPC space for a while, that networking, especially for many of the distributed applications, is so core. And this is, again, where we took the best technologies that existed on premise and really think of not just building a system on its own, but really thinking of building clusters that perform well as a joint system together to deliver the value and meeting the needs of the very demanding performance. There's high performance storage and workload orchestration. Outside of my team, we work super closely with these teams to ensure we have a complete that meets the performance needs capabilities. Then you're not delivering the full value, and this is where we work super closely. Under workload orchestration, and each one of these will have its own sessions and deep dives, so I won't go too much in them. Workload orchestration is also super important to enable the transitions of content, and moving the workloads and making sure that both different levels of capabilities are available for users to move forward. So moving forward, looking at our actual fleet and thinking of how do we think of all the various offerings we have in compute. So if you look at my team, that's kind of the H&N, which will be the focus of this session. But Azure is actually made up of a broad spectrum of offerings in terms of compute capabilities. And even on the left-hand side, where you think of A, B, D, and F, and L, and M, these are what we consider general purpose hardware, but you can see there's a lot of differentiation there as well, from running on high memory, on compute bound, things that are IO bound. And this is where, and then you move into our section, which is all about specialty built hardware, where we bring in things like Infiniband, things like the accelerators, to the bring into Cray, which is a bare metal offering in Azure that can extend where our SKUs kind of end off to provide a continuum. It is not uncommon for a lot of our customers to run across many of these different offerings, basically picking the best of the offering for whatever workload and whatever stage of the workload is actually applicable to the customer. So, just because it comes from outside of our team, outside of specialty, that doesn't mean there aren't great choices for running part of, small scale MPI or embarrassingly parallel simulations kind of workloads on the rest of the fleet. So that's something else just for you to be aware and aware as you pick and choose and guide customers towards this.
So as Jack mentioned, the area where H and N VMs on Azure really differentiate themselves is their ability to run demanding problems at scale. At levels of scale, frankly, that for a long time the public cloud has been unable to, and much of the market, including partners, have not expected public cloud to be able to support. Our team in Azure is built around the notion of upending that notion and that narrative by delivering capabilities more befitting not just on-premise clusters, but bare metal on-premise world-class supercomputers. And you can really see the results of that intent and focus and investment from the Microsoft side in some of the milestones that have occurred just inside of the last few years. A couple years ago in 2019 at ISC 2019, we got a lot of attention and caught a lot of people by surprise by running the first ever 20,000 core MPI job on the public cloud. And to put that in context, that was at the time about 10 times larger than anything that had occurred on the public cloud to date. And we did that with one of the core application acceptance tests of Prace over in Europe. Then later that year, we injected two new technologies that have been the foundation of many of our specialized computing programs since then. The first is we were the first public cloud provider to put AMD Rome into our fleet for the purposes of high performance computing and other advanced computing use cases. And we coupled that with the public cloud's first and to date only 200 gigabit HDR InfiniBand deployments. This second piece is really, really critical, because what this meant was Azure was a time to market leader with a interconnect technology that was as good as the very best as the state of the art could be providing to any leadership class supercomputer and supercomputing site on the planet. And we brought it time to market, put it in the hands of all of our customers. And that enabled us to go forward with some of the really big accomplishments that we then furthered in 2020. You may have seen the headlines around the fact that we ran an 80,000 core MPI job, first for weather modeling and then again for biophysics. And then a lot of attention was paid to us because we became the first cloud provider to demonstrate that we could run a 1 terabyte per second file system on top of this technology. And then all of that goodness became derivatives that got plumbed into our latest offering, the NDV4 that Jack mentioned, for our leadership class AI training offering on Azure today. want to dive a little bit deeper into the networking because this really is a core piece of differentiation between not just Azure versus the other cloud providers that you have the ability to partner with, but also as you fundamentally engage a market that is today 80 to 90% still on premises and is looking for data points, proof points that Azure and the public cloud can support their workloads at a highly performant level, scale efficiently, and return maximum ROI for that scale. So how do we do InfiniBand on Azure? The simple understanding is we do it as good as you possibly can. So we start with 200 gigabit InfiniBand HDR networking, as we mentioned, and we build it in a non-blocking factory. That means there's no oversubscription on the network. And then we present it into VMs via a technology called SRIOV, which means that the InfiniBand network adapter is passed through on a bare metal basis. You as a customer don't run a synthetic driver or some abstraction of the card. You run standard Mellanox OFED drivers, exactly as you would on a bare metal on-premises cluster. And we even build and support pre-optimized operating system images with those drivers built in if you just want to grab and go, get up and start running InfiniBand jobs. We then inject some additional goodness into what we do with InfiniBand on Azure that even customers who are running InfiniBand today are likely not to have. A really key attribute of that is adaptive routing. Adaptive routing is intelligence built into our InfiniBand switches that automatically load balances traffic in the most performance optimal way possible. It avoids points of congestion and enhances maximum data flow so that when you run scaled applications, you get the best possible performance. In our testing, we see a 17% speed up for at-scale workloads just by using adaptive routing. It doesn't cost anyone anything extra. It's just a feature there that you are free to use, and it gives additional performance at no additional cost. Another thing I would call attention to would be hardware offload of MPI collectives. And you may not know what that means, but here's what it means for you and your customers specifically. More performance for less cost. When you run an MPI application, the compute time of MPI collectives has to be done on CPU cores themselves. You don't want them done on CPU cores. You actually want them done on the onboard processor of the Mellanox network card, which is purpose-built to do that computation. In our testing, we have seen as much as a 2.1x speedup simply by using hardware offload of MPI collectives. What that translates for you with your customers is you can say, customer, you have a licensed application. Let's say you run on 4 nodes in Azure. If you come to Azure and you use this hardware offload of MPI collectives, you can get double the performance for your software licensing investment. Or conversely, you can get the same amount of performance for half as many software licenses used. That's tremendous value for so many of our customers using licensed applications. And then the last piece I would especially call out are some things that are really important, especially for our newest GPU offerings, which is we have direct nickel integration from NVIDIA's driver stack, as well as full support for GPU Direct RDMA. So I'm going to spend a little bit of time now focusing on our H-series CPU-based VMs that I lead inside of Azure as part of Jack's team. And that includes our HB and HC series of virtual machines for scalable HPC workloads. So the HB V2 is our second generation HB line of virtual machines, and quite simply it's the most powerful HPC offering not just in Azure but in the public cloud. It features the top of the line AMD EPYC second generation processors, otherwise known as Rome, with up to 4 teraflops of compute power, and really critically 350 gigabytes per second of memory bandwidth, where in our view, you can really see that most HPC workloads scale in line with the amount of memory bandwidth that can be delivered to an application. So us supporting the state-of-the-art from a CPU-based memory bandwidth perspective is very, very critical. And we're proud to say that there is a 100% performance delivery of memory bandwidth in our virtual machines as compared to bare metal. This comes with our 200 gigabit HDR InfiniBand network that I just mentioned, as well as NVMe block storage access. We also offer, because we are not a provider of a single hardware platform often, but we want to provide customers different choices for different scenarios and sensitivities. What we believe, and have good data to suggest this, is the leading Intel-based cloud HPC platform. It features Intel Xeon Platinum processors with 100 gigabit InfiniBand networking, and once again, the top-end memory bandwidth support on an Intel-based Xeon Platinum platform. So customers frequently ask me, okay, help me understand what you're doing on Azure with these specialized instances as compared to what else is happening on the cloud. So what I commonly tell people is the real big difference is on other public cloud providers, what you will find is a series of general purpose virtual machines that a cloud provider will say, this virtual machine family can run a dozen different workloads. You'll look at the product page and you'll see many different classes of workloads, many of which are things that you associate the cloud with, like web services. And that makes sense. That's a lot of what the public cloud serves from a customer standpoint. And so that is their design intent with a lot of those offerings. So let's take a look at 3 different offerings from a leading cloud provider, Amazon Web Services, that they position for high performance computing services. We have the C5N, which was Amazon's high clock frequency Skylake platform, their C6GN, which is their 64-core Graviton2 ARM platform, and their 24-core M5ZN platform with high frequency Cascade Lake processors. All of these we are picking because they feature Amazon's very best networking, 100 gigabit EFA. Let's take a look at how both of these, or all of these offerings from Amazon do as compared to HBB2 and HC, which are purpose-built for HPC. We're going to look at a benchmark called Spec CPU 2017, and specifically we're going to look at spec rate floating point. And the reason why we do that, there's no one benchmark in HPC that covers all scenarios, but Spec CPU 2017, especially on the floating point side, is a pretty good proxy for us to look at because it runs 14 real-world applications across 13 scientific and engineering computing domains, which means that there's almost assuredly an application tested in here that is going to have direct relevance to the work that an Azure customer is trying to do. On the left, you see a depiction of raw performance. Higher is better. What you'll see is that the Amazon performance is all lumped around roughly the same levels of performance. 3 different offerings, 3 very different flavors allegedly, but they're all within about 20% of performance with each other. What's the commonality? They're all slower than our slowest quote-unquote HPC offering, HC. And then when you look at our HBB2 offering, you're looking at a nearly 3x performance advantage as compared to what Amazon is putting forth, even with their custom in-house Graviton architecture. When you overlay that with a statement of what's performance per dollar look like, what is the actual return I get in the investment for every dollar I spend on Azure as compared to a leading cloud provider, the story doesn't really change. You'll see that the Amazon data points are all fairly closely grouped up with one another, but the refrain still holds. HC still has a clear and convincing lead over both of the x86 options on Amazon and even Amazon's new Graviton offering. Meanwhile, HBB2 ends up in a class all by itself, nearly 2.5 times the performance per dollar as compared to the lowest performance per dollar offering on Amazon. Finally, let's take a look at scalable performance. This is where we really set ourselves apart and where our investments in InfiniBand networking really come into play. If you were to look for the largest scaling demonstration on the public cloud, on any other cloud provider, you would find a data point that happened to run on Amazon, could have been any cloud provider, of about 7,200 CPU cores. Well, we've run workloads that are 12 times that size. And that isn't our limit, that's just where we happen to stop. And what you see here is that we're running this not just on one stunt benchmark, we're doing this on real world workloads from a broad variety of scientific and engineering domains over time across both HC and our HBV2 offerings. From quantum chemistry to graph analytics, we submitted the number 17 all-time score to the Graph 500 for Supercomputing 2020. Star CCM, an extremely popular fluid dynamics application. WRF, which is one of the most popular weather modeling applications, and finally NAMD, which is probably the single most popular molecular dynamics application. We did this work with the University of Illinois and the Beckman Institute, and I'll talk more about that in our next slide. So let's stop looking at other cloud providers, because let's be real, most of the customers you're going to be engaged with as partners are coming from some version of a bare metal on-premises context. And the litmus test for you as a partner is showing them that the cloud provider that they would run on top of can meet or exceed the best on-premise construct that that customer could provide for themselves. Here's Azure going toe-to-toe with Frontera, one of the top 10 supercomputers in the world, and the U.S. National Science Foundation's Track 1 supercomputer. This is the second most powerful CPU-only supercomputer in the world, and we ran, the team at the University of Illinois, the Beckman Institute that develops NAMD, ran on Azure and on Frontera. So Azure had no involvement in the data collection whatsoever. And in an identical NAMD version 2.14 test, Azure came out 40 to 90% faster than Frontera at an equivalent number of 512 nodes, or about 60,000 CPU cores on Azure. A couple of really important takeaways here. First is, this is pretty clear and convincing evidence that now Azure is putting world-class supercomputing capabilities at the fingertips of every single one of our customers. The second thing is, I would again note, this wasn't for a stunt. This was with the Beckman Institute, which is being sponsored by Azure and the White House as part of the COVID-19 consortium to take high-performance computing resources all over the world to model and simulate the SARS-CoV-2 virus. So this is not just a case of us demonstrating super compelling performance and scalability even against a world-class supercomputer, but doing it for a highly applied, critically impactful workload for our customers.
Thank you, Evan. So continuing looking at our offerings, we're going to switch gears a little bit and talk about our GPU-based offerings across our fleet. And at a high level, you can think of these really falling into four main workloads that we're trying to target and really provide optimized capabilities for: visualization, rendering, HPC simulation, and deep learning AI. And to support these multiple workloads, we actually have three of our main product lines, NV, NC, and ND, which is part of our accelerated computing. NV focuses on graphical applications, and this is your virtual desktops and workstations accelerated computing. It also falls into some of our gaming-based offering. NC is our general purpose GPU compute, and these are the more flexible sizes with broad global footprint VMs designed for lightweight and mid-range AI, analytics, simulations, and rendering. And finally, there's ND, which is the scalable deep learning. And these are really the specialized SKUs for distributed AI training, where we leverage many of our capabilities that Evan talked about on the HPC SKUs, specifically the very tight internetwork connectivity within the cluster to provide optimal capabilities for the requirements of these workloads. So let's walk through the various offerings in this area, in this space. We're going to start with NV, which is our graphics application-based systems. So when we think of graphics application-based system, this is also something that has specialization even within this space. So, the pyramid and the numbers here aren't as important. Just the fact to realize that there's actually multiple use cases that we're trying to cater and provide best offerings to. On the bottom, we have basically the desktop workstations for knowledge workers, and this is kind of the simplest entry level of a GPU accelerated based workstations. About 2 gigabytes of GPU frame buffer, low end 4 cores per system is the kind of capabilities most users will be satisfied with. Then in the middle, this is the designer workstations. This is probably where we see the bulk of the usage on our fleet and bulk of the demand within the NV series. And this is things like CAD applications, seismic interpretations, things like Petrel, and this is where your memory goes up to about, a quarter of a terabyte. You have pretty modest requirements in terms of CPU and I/O speeds. And then you move up higher, which is really the high-end media entertainment, high-end design workstations, where your ratios change from up to half to 1 terabyte of system memory per GPU. This is power rendering, again, seismic interpretation. What you can see is some applications like Petrel actually fall in both buckets, and that is because it's a function not just of the application, but the kind of models and data you're working on that determines the need of the system. And the other thing that's also key to call out is that while these are graphically accelerated systems, the entire system balance is what matters. So system memory, the number of cores, all make up the requirements of what's required here. Our two main offerings in this space are NVV3 and NVV4. And despite the fact that one says V3, V4, that's more of a naming limitation that we have had in some of our SKUs. These are actually both current offerings within this space, so don't let the version differences skew your decisions. Both of these are leading capabilities from across our two key hardware partners to bring in their innovations in this space across the offering. So let's look at one of these. NVV4, which is our AMD Rome plus Radeon MI25 GPU. This is one of the unique things about this offering is that this is a first of its kind in the cloud, where we're actually taking a technology called GPU partitioning, where we actually can take a single GPU and then actually partition that with a secure, fully dedicated capabilities mapped into VMs, which means you can use a full or a partial version. And why would you want to do this? The main benefit for our customers is that you can right-size the actual system to what your needs are, meaning you are fully cost optimized to using the resources your application really needs. And the nice thing of running things in the cloud is if you need a bigger system, you would just go and deploy exactly the same image but on a bigger size, and you have now doubled or tripled or quadrupled your actual GPU system resources and that have scaled with the rest of the system. This offering continues to evolve in terms of coming in with new features, things like Linux guest OS support hardware encoding, and additional OS versions. This is another example that while the hardware may land in our fleet, we continue to invest and provide more value from the capabilities to our customers as part of ongoing investments. All right, so let's quickly look at NC and ND, which is more on our compute side, based on the accelerated part of the fleet. So we'll start with ND, and this is really where we focus on AI workloads. These workloads have grown hugely over the last N years as we've had these offerings. It's actually interesting that it's only been 5 years since the first introduction of GPU accelerated offerings in Azure and in most clouds, yet you can see how much we've invested in terms of creating different offerings across each year. This market has been growing super fast in terms of specialization, and today we see there's at least 3 mature workloads within what we consider the AI space. First, there's real-time inference and low-cost compute. Next is mid-range training and dense inferencing, and distributed high-end training at the bottom. And these are continuously evolving, where we definitely see new and other workloads that are beginning to mature in the space. And what this means is every time we actually have the capabilities come together, we will invest in having a real, having a specialized offering to meet the unique capabilities of this need. And this is again following the same theme of specializations and ensuring that we can deliver the right hardware optimized to the needs, unique needs of the workloads. Beyond the hardware, it's useful to call out that we take specific planning in terms of how we even treat capacity footprints with the requirements of the various workloads. For some workloads that are more real-time, we spend resources in deploying these more broadly across our many data centers to bring in the compute closer to the customers, while other workloads, which are more less sensitive to latency, can be but much more sensitive to having a large, dense compute very close together, are deployed as large clusters of compute as part of this. So let's look at some of these offerings making up these capabilities. So our T4 offering brings the T4 NVIDIA T4 Universal Deep Learning Accelerator to Azure. As you can see, we've also paired this with AMD Rome EPYC on the CPU, plus the NVIDIA GPUs. This has resulted in some interesting capabilities for our customers that differentiate the offerings on Azure. First, you have a very high core count to GPU to enable processing and doing a lot of CPU-based preparations before you do the GPU computation. The other thing to point out is everything in our H series together with our NC and ND, we do not enable hyperthreading, which means the core counts we're providing are actually physical cores available to you and aren't hyperthreaded enabled. And this again is based on our insight into the workloads and optimizations behind to ensure that we can provide maximum value and performance. The last thing to call out about the SKU is you can see that we offer this in variable memory and core configurations per GPU. And that is again enabling different price points for optimized usage, taking into account the multiple use cases that would be used on a SKU like this. Where here this is ideal for inferencing, video encoding, and lighter GPU compute scenarios. So let's look at something very different, which is our latest offering called NDR V4. And this brings the latest flagship NVIDIA offering, the Ampere line of GPUs, to our fleet with a high-end AI-based system. This is comprised of a dense 8 Ampere GPUs in a single system, interconnected with NVLink and NVSwitch into a very powerful node in itself. But we don't stop there. We also pair that together with the latest capabilities from Mellanox in terms of 200 gigabit InfiniBand, and that's per GPU, meaning you are able to get 1.6 terabits of dedicated InfiniBand interconnect across the cluster, separate from the front-end network. And these are the kinds of capabilities that differentiate our offerings in terms of providing unique solutions that are meant to meet the most stringent requirements of these workloads. Something else to call out here, when we looked at the system, we actually went back to the drawing board and designed this from scratch in terms of a custom ground-up system to ensure we can use latest technologies, things like PCIe Gen 4, to ensure end-to-end best performance across the full system. So looking at this, the unique things that has really transformed is, we're slowly start offering scalable AI supercomputers as what's offered in Azure. And if you take this SKU as an example, where we start with a single A100 GPU, then put 8 of these in the system, PCIe Gen 4 AMD Rome-based processor, you have a very powerful node. Then you bring in NVLink for tight interconnecting within the node itself, where you have 2.4 terabits of full duplex non-blocking bandwidth within the system itself between the GPUs. And then on top of that, you bring in Nickel together with HDR from Mellanox to enable scalability across the cluster. What you are left with is a very scalable AI supercomputer that is delivered to the masses. And now anyone in the public cloud space can come in on Azure and have access to an AI supercomputer. Could it be one node and scales to hundreds GPUs or thousands of GPUs? It's really based on the needs of your workload and is available worldwide in many locations. So there's a few more links here for both how to join. This is still in our preview program, and also more information on the program. So I'll close off with an NP, which is our Programmable Fpga series. And this is where we have an offering including our Xilinx partner, where you have the flexibility of 1, 2, or 4 Xilinx U250 FPGAs brought together in a single system. The unique capabilities here is we work closely with Xilinx to ensure the same shell and capabilities, which means you can develop on-premise, develop your bit streams, debug them, and then move them to the cloud when you're ready. This is also another example of us ensuring that we bring in a broad set of offerings for unique capabilities. There are certain workloads like genomics and life sciences or big data analytics that really benefit from the unique capabilities of an FPGA, and we want to make sure we have a rounded portfolio of options to our customers to take full advantage of this. So in closing, we want to just touch a point about partner engagement and some of the best practices. And best practices is one way to put it, but just things we've seen to work really well in our engagement with partners. First of all, we encourage you to really be workload and vertical specialization. This has been a great expansion of our team, where we rely on our partners to provide that workload-based capabilities and vertical know-how engaging with the customers. It resonates super well with the customers and becomes a natural extension of the specialization of what we provide in Azure, and bringing that knowledge into the customer language, into customer scenarios. Second is leveraging best of Azure for maximum customer value. As you've seen, our portfolio is broad and evolves quite quickly. Understanding the various offerings and how it maps to the customer's specific workload needs, or even stages in the workload, can become highly powerful for you to create a best of Azure and best of your solution. This also means there's a call out to our partners to ensure that they quickly adopt some of our new offerings to bring the newest innovations as part of a single solution. And finally, connect with the Azure team. We're here to partner, learn, listen, and engage, and basically bring together the most powerful of Azure and your solution to our customers. So, we look forward to working with you, hearing from you, and that's a common theme across the number of sessions and been a number of opportunities of how you actually engage with us to make sure we continue to stay in dialogue beyond sessions like this. Anyway, I will end with this and hand it off over to you, Mark. Thank you very much. Thank you for the opportunity to speak with all our partners.
Thanks, Jack. I really appreciate it. Thanks, Evan, as well. And just to kind of reiterate, here I'm just bringing up the next session. Just to reiterate what Jack was saying, we're here to partner, obviously, and we encourage. I've been part of this Azure HPC ecosystem for about 3 years now, and it's just it's a tight-knit group. We're eager to partner with our own, just internally, but also with you as our external partners, and whether it be a sales engagement discussion or an engineering product discussion, whatever that may be. So let's make the transition. Our next group is from our storage engineering, our storage product management team. And we've got Andrew, Klaas, and Scott. They're going to do, I know, a fantastic job of really taking everybody through all the different options. And it's, storage is funny. There's, it's not one size fits all. There's a lot of different combinations, And these guys are experts, and so obviously hear what they have to say, but also provide the opportunity to ask the questions, and we'll try to get you the answers. So, Scott, I'm going to let you drive, and if you remember, you got to put it in presentation mode so that people can see the fine pitch font that you provide us, right?
Mark, I can't believe you pointed out the flaw from my earlier presentation. Okay. Let me know if you can see it all right.
Yes, I can see it, and I can hear you just fine. See you and hear you just fine, so thank you very much.
Fantastic. So thank you, everyone, for joining. And this is going to be a 30-minute session that discusses a few items around our storage engineering, specifically around a handful of products, and also any questions that you may have in flight. Please reach out and don't hesitate to ask while we go through this session. As Mark said, I'm joined by Klaas Langhout and Andrew Chen, both PMs in the storage group, and we're going to be talking about advancing slides. There we go. Blob, Azure NetApp files, and a service called HPC Cache, giving you updates on the roadmap. In particular, we're going to start out talking about blob storage and some areas around blob storage that make it really exciting for some of the HPC workload opportunities that you might have. And with that, I'm actually going to hand it off to Klaas now, and he will walk you through. So Klaas, take it away.
You betcha. Thank you, Scott. So on the blob storage side for high-performance computing, the first thing I want to talk about is the Nfs V3 Protocol. We have this in preview right now, and this extends what we call our multi-protocol capabilities, where on our object store we are lighting up not just the Blob REST protocol, but with Gen 2 we add a hierarchical namespace and the HDFS protocol, and now in preview we are adding the NFS protocol as well. And so that allows HPC type jobs that do use the Nfs V3 protocol to make use of blob storage as being a highly elastic and low cost solution. Talking about performance and scale, we have an SSD based tier, only public cloud that has it, which allows, we call it premium blobs, and that allows very good small object performance and much lower latency. With our premium blob stack, we see latency on the order of 5 to 8 milliseconds, whereas our standard hot and cold tiers are around 50 to 55 milliseconds of latency. We are raising our account limit all the time. Right now we are in the midst of raising it to 60 gigabits per second and then also 80 gigabits per second. That's for egress. And we are on our way to what we call limitless, which will be a much higher number by the end of this year. We'll see exactly where we get to, but the numbers that we've been discussing are on the order of 0.5 terabits per second ingress. High throughput block blobs is a feature that we rolled out, I think it was about a year and a half ago, where the naming of the object, so the storage account, the container, and then the fully qualified name, is less important. You don't have to think about it from a partitioning standpoint on our side. So at that point in time, if the object was greater than 4 megabytes in size, you could call it whatever you want, and we would make sure that we partitioned it correctly for optimal ingress performance throughput. We're in the midst of lowering that to objects of 256 kebytes in size. So it'll just make it that much easier. We don't have to think about the naming. We also in preview and should GA shortly have raised our maximum file or object size. It was 5 terabytes. It's now 200 terabytes. This comes up mostly in oil and gas and media and entertainment, where they do have very large files that they want to deal with. So instead of breaking those up in multiple files, they can just use the file natively that they would on premises. That also comes in with an increase on the individual file size that you can put up to 5 gigabytes, if I remember correctly. Last on performance and scale, I wanted to just mention Blob Fuse. It's an open source component that we manage and provide updates to. It allows a Linux guest or VM or container to host a remote file system, which happens to be a blob container. And so that blob container will read and cache locally on that Linux host or VM, and then all of the processes on that Linux can interact with that data cache as if it were, well, it is a local store. We've seen a fairly high amount of usage for AI-based workloads, where the number of reads are very high, and they want to cut down the latency to a remote store to the minimal amount, which that local cache does quite nicely. We are enhancing our resourcing for Blob Fuse based upon the growth that we've seen in AI-based workloads, and that could also be used for just any generic HPC workload. Lastly, on management and cost control, I wanted to mention that we have something called lifecycle management, which allows blobs, versions, and snapshots to be tiered from hot to cold and to archive in a reasonably seamless way, and also deleted. We are adding to that last access lifecycle management, where instead of it being a last modified condition, it can be based on the last time the file or blob was accessed. And so that allows a much easier paradigm where you don't even have to know what the pattern is. You could specify after 90 days, go ahead and move it from hot to cold. After 180 days or 181 days, move it to archive. And then after 2 years or 7 years, go ahead and delete that object. Inventory is a feature that makes it much easier to get a listing of your entire storage account, even if it was billions of objects. You can specify it to run once a day or run once a week, and we will create either a CSV or in the future a Parquet file format of all of the objects within your storage account, or a filtered set based upon a prefix that you provide. And so that provides a much easier way to get a catalog or inventory listing of the objects in your storage account. And last, one of the common patterns is to use a columnar database or a SQL or Cosmos DB to keep a catalog of all of the unstructured data that you store in object storage. Index or index tags allows you to add up to 10 indices per object and then do a query directly against the object store to return that subset of objects. And so that precludes the need to have that separate catalog for some use cases of using blob storage. So I wanted to mention that just because it reduces the complexity and makes it lower cost as far as providing a full end-to-end solution if you were using blob storage for HPC workloads where you wanted to do other sorts of processing and management against that data. Scott, I'll turn it back to you to get down.
Yeah, so a couple of questions. One came across the wire here asking about what the current maximum I/O rate someone could expect for the NFS solution for like a single virtual machine accessing it. Do you want to speak to that at all?
So from a single virtual machine, and Klaus and Scott, go ahead and chime in, I think that the limiting factor would most likely be network. And it also depends if it's multi-threaded or not. We're working hard to make sure that the NFS protocol doesn't add any arbitrary speed bumps to what you can do with raw throughput. The NFS protocol tends to have smaller block sizes than what you could do with the Blob REST protocol, so that will actually impact overall throughput. On a premium block blob storage account, for instance, if that's being used with NFS, the default TPS that we dial in is 100,000 TPS. That number can be pushed up based upon request and what other things are happening on that storage stamp that account happens to reside upon. So we do have some flexibility there, but I think that's going to be more of the bottleneck.
Okay. Thanks, Klaus. And then Evan, you had also answered the question about, there was a question about Infiniband access and the answer to whether or not you could use storage with Infiniband. And the answer that Evan put forth is we have published a BGFS, roll your own BGFS deployment model that you can leverage. And that actually was something that we can certainly share with folks out there. Our Azure CAT team engaged in that build out as well. Are there any other items or features, class, that you wanted to mention relative to HPC?
I can mention it's not really HPC per se, though. I was going to say that we are working on a roadmap of also adding an SFTP as yet another protocol where you can access the object storage directly without using protocol gateway, for instance, which will just make it that much easier to basically glue in an HPC workload with an other larger workload as well. I think that's about right.
Okay. Yeah, so just to sum up, this is really exciting, and for the partners, this is really what makes Azure Storage unique and distinct from the competitors, is this implementation and leveraging of the namespace. This is the sort of holy grail of storage in the cloud, where I have price performance tiering support through things like lifecycle management. I have an archive tier, but then I can also present the data in a variety of protocol formats, not just REST. And with the NFS capability coming, I don't have to add an additional layer of logic at the VM to realize that ability. So that's really an exciting development with regards to Azure Blob Storage. So with that, I'm going to hopefully advance the slides cleanly. And we're going to hand off now to Andrew Chen, who oversees our Azure NetApp Files offering. Andrew, take it away.
Yeah, thanks, Scott. So a number of Azure NetApp Files updates since the middle of last year. Leading off with one that's definitely of interest in the HPC space, particularly in oil and gas, is we do now offer simultaneous multi-protocol access to the same volume over NFS version 3 and SMB. So this was definitely a highly requested capability that is now broadly available. And directionally, we are working to expand the protocol support for multi-protocol access in the future. A couple things related to performance. Two preview features that we introduced is one, the ability to move a volume from one pool type to another. So, that gives you the opportunity to get more performance or destage cooler data, say if you want to move from, a volume from premium tier up to ultra or down to standard, giving more flexibility in price performance. And it does not require a data copy and can be, in fact, done without interruption in access to the data path. So, one dimension in terms of performance flexibility, and then another one is we introduced the flexible QoS type pool, which allows, if you have a volume within this pool, previously the allocation of bandwidth to capacity was at a fixed ratio based on the nature of that pool. So for example, in Ultra is 128 megs per second for every, terabyte of allocated capacity. With the flexible QoS pool, you have a gross budget of capacity and of bandwidth within the pool, and you can allocate those separately to the volumes within the pool. So for example, if you have smaller, hotter volumes and then larger, cooler volumes for a mix of workloads in your deployment, it now gives you the ability to minimize over-provisioning by balancing how you allocate those dimensions. From a data protection standpoint, two key capabilities that we're working on. One is cross-region replication, the ability to replicate data across Azure regions, which is in public preview. For those who are familiar with NetApp technology, it is based on their snap mirror replication, so very efficient block level incremental snapshot that also carries full fidelity to the data protection volume in terms of metadata, ACL, snapshot chains, and whatnot. From a regional availability standpoint, it's not any to any, but for most regions, we offer at least one, if not multiple, replication choices. So there's some flexibility versus a completely fixed pair in the case of many regions. And this does use the underlying Azure network for network transport. It's not routed through, say, your customer VNet over customer network connectivity. And then we're also working on an integrated backup capability, so a feature we call ANF backup. That will leverage more cost-effective storage on the back end, so enabling you to back up data or destage larger data sets into a lower tier and provide data protection. So that feature is in a limited private preview right now, which will be expanding in availability over the next few months. On the security side, we introduced client-side encryption for NFS version 4.1, and we will be working on enabling that for SMB protocol as well in the future. And then just in terms of sort of expansion, we do now have Azure NetApp files live in 3 major gov regions in the US, so Virginia, Texas, and Arizona. And we've also been working on building out our portfolio of certification. So, in the gov space, we have FedRAMP High, IL5 certification. We also have IRAP and, SOC Type 2 certifications as indicated in the chart.
Okay. And any questions for Andrew on Azure NetApp files? Okay, I'm not seeing anything in the dialogue, Andrew, so I believe that will be it. Thank you.
All right. Thanks, Scott. Thanks, everyone.
All right. And so the last capability we're going to talk about today is HPC cache. So this is just a reminder, if you've not seen this service before, it's a little bit of a different capability. So you had heard Class mention Blob Fuse being a caching capability that you could deploy on, looking at the left of the screen on the individual HPC cluster nodes, and they would provide nice local access of blob-based data. The difference here is this would be more of a centralized cache cluster that really gives some unique, distinct capabilities that certain customers who have concerns around geographic location of data, for example, or are not simply ready to move their data from their on-premise environment, they can take advantage of this capability, this high-performance cache. It sits in Azure as a first-party service. It's fully manageable through ARM, through Terraform, and through other capabilities. And it provides some key things. One is performance by offering low latency on-demand access of byte ranges of data. So by contrast of if you have a lot of data on-prem, one way that you bring that data up from on-prem would be to copy the data onto the individual nodes and run the jobs. The way HPC cache works is rather than having to acquire the entirety of a file, you can get the byte ranges of the file based on what the clients request. In addition, it does offer a pseudo-root-based namespace that you can plumb in exports from NetApp environments that might be sitting in your data center or Isilon or other NFS environments, as well as being able to bring together even ANF volumes, or if you have a need for a low-cost blob-based NAS solution, we do offer something called Blobs POSIX, which provides 100% POSIX compliant access. It supports things like hard links and other capabilities which aren't always supported by file system solutions in the cloud. And so this is just to lay the groundwork for what HPC cache is if you haven't seen it. Another important distinction is this is not a provisioned storage model. By contrast, to get the bandwidth and throughput out of other storage solutions, you would provision a certain amount of storage to achieve the bandwidth. This is a little bit different. You provision based on the anticipated performance, and you can go from 2 gigabytes per second throughput up to 8 gigabytes per second throughput today. With all that in mind, here are the updates in terms of things that we've recently done. We also have supported Fairfax, which is the U.S. government public cloud, both East and West. We've also added a series of regions. In terms of APAC, we've added Korea Central. We are almost finished with adding, I believe, East Asia as well. So we're in a lot of places in APAC with the service. We have made significant availability and performance improvements, in particular our uncached read performance. For information, uncached would be the cold reads from, if I refer back to that diagram, reading data from the far right of the screen into the cache. That particular time we've been improving over time, and also failover. So this is a highly available cache, which means there are multiple underpinning systems that constitute the cache. in the event an individual node fails in the cache, the IP addresses are reprogrammed. Clients never go down, but there are outage impacts felt, sort of dips in performance, and so that's what we're talking about here in terms of outages, a dip in performance, and we've been driving that number down and further over the course of the past several years. We've also introduced support for double encryption. Double encryption would be the encryption of the cache disks themselves, with the additional ability of supporting key vault-based customer managed keys. So you could put your own key into Key Vault and it's integrated and it will encrypt the cache disks. You can rotate those keys as well. We do support there's this capability called encryption at host, which is basically encrypting the transport between data centers. So anything that travels on what we'll call public wire, so that would be between data centers, gets doubly encrypted with that transport encryption. We recently introduced support for auxiliary Nfs Groups. So if you have a need for going larger than 16 Nfs Groups, that is now GA in HPC cache. You can source the group definitions and mappings through a standard file or LDAP, or you can integrate with a non-Azure Active Directory. So you'd have to set up a domain controller synced with your on-premise environment and be able to provide it that way. We've also introduced something called client access policies, which are equivalent to something like an export policy in NetApp, and that can actually be applied per junction. If I refer back to the diagram, junctions would be these directory structures that are plumbed into individual exports. So you can actually control based on network or host at the junction level in your namespace. And these are just a couple of screenshots to give a feel for what that looks like in the system. You have the ability to root squash and map to anonymous IDs as well. And this is just a screen of the actual source of data. And then the last screen that we have here is referring to something a little bit more akin to parallel file system solutions that you might be looking for in a high performance environment. So we've been working very closely with Cray over the course of the past couple years, building out what's called the Cray Cluster Store solution. And so this is a deployment of Lustre built out on bare metal, deployed in Azure data centers. This is dedicated. This is not a shared service, so as you can see, the performance and storage are fairly large, and so these are really meant for an overall dedicated deployment of Lustre. If you have a large enough solution that you need to run in Azure, you can get up to 45 petabytes of raw storage and up to 460 gigabytes per second of aggregate throughput speed. And I think that would be it. There seems to be a couple of questions in the dialogue here, but... or maybe not. Okay. So I think that the Lustre file system is connected over Ethernet. It is not IB at this point. Okay. All right. Well, with that, we're going to close out the storage section. We really thank you for your time. And if there are any subsequent questions after this session, please feel free to reach out and we'll get you the answers. Thank you.
Okay. Thanks, Scott. Thank you, Andrew. Thanks, class. That was another fantastic session. Really appreciate it. So next up, we have Rob Futrick from our computer software strategy. So Rob, I kind of see you there. Rob Futrick?
Can you hear me?
Yeah.
All right. Nothing like Bluetooth headset fun. Second.
Your camera.
All right.
Much better. Look great.
Share my screen. Excuse me. Thank you, Mark. So I am Rob Futrick. I am the Principal PM Lead for Azure's HPC software and services. And I came to Microsoft about 3.5 years ago as part of their acquisition of Cycle Computing. And I was at Cycle for quite a long time. And so I've been doing cloud HPC for 14 years now. I think probably about as long as anyone has. And I've seen quite a bit. And so here today to give you not just kind of a feature review of the products and services, but I want to kind of communicate the philosophy behind what we do so that you have an idea of how we approach our entire platform, as well as it gives you some insight into where we're headed with it. So this slide always kind of makes me chuckle because I've been delivering some version of this slide for a very long time. But you know, I think everybody here has probably heard some version of this. But basically, why do people look at cloud? And in particular, why do HPC customers look at cloud? And in general, from a high-level perspective, they want to get more agility or more speed, and that could be either access to technologies that they don't have on a faster time frame, so some kind of business agility, or infrastructure somewhere in the world that they don't have a presence. It could also be running their workloads faster or more frequently or at greater scale, basically giving them faster time to results and some kind of business agility or engineering agility. Or it could be scale, just the ability to actually deploy and run at levels of compute, levels of storage, et cetera, that they did not have access to on-prem, which is perfect for burst use cases. People want to supplement their on-prem capabilities. As Evan had mentioned earlier, and as you'll hear pretty much everyone say, we don't view most of the industry as being kind of cloud only. It's really supplementing their HPC on-premises environments with cloud capabilities. And then for those that do actually want to not deploy, let's say, another data center or consolidate, et cetera, then you do have people who look to cloud to migrate workloads entirely. And so for many years, the refrain has been, well, why aren't they? Or what is keeping people from running in the cloud? And historically, that has been cost performance, simple and performant hybrid file access, and really just management of data. And then finally, the last one being just the complexity of doing that. And kind of the sessions today have hit all three of those points. So obviously our VM offerings and our storage offerings cover both the first two, the cost performance aspect, and the data management, data transfer, and hybrid file access. And HPC environments already tend to be at the limit of our partners and our customers' kind of technical ability. And that's not a criticism, that's really more a reflection of how optimized those environments are. And so if people get more budget, they get more capabilities, they get more expertise, then they just make their HPC environments that much more complex or more efficient. And so the problem then becomes, if we tell people you can come to Azure and you can get this fantastic agility, this fantastic speed, unimaginable scale, and we can manage technologies for you or work with you to make hybrid environments, et cetera. But there's all this additional complexity that becomes a non-starter. It's like the old programming adage that debugging is twice as hard as programming. And so if you put all your cleverness and all your intelligence into writing the code in the first place, almost by definition, you can't debug it. And so what we are trying to do in the software platform is give you access to all that amazing compute that Evan and Jack talked about, all that amazing storage that, that Scott and Klaus and Andrew talked about, and remove the cloud complexity from that. Give you HPC level abstractions for how you access and how you scale and how you actually get that agility, speed, and everything else. So what is our resource stack in Azure? We already covered the bottom, which is the compute series, the storage, and then the networking that ties it all together. So that kind of describes what the Azure, conceptual, let's say, data center that you're renting is, or that you're deploying into. And then how do we actually make that easy to orchestrate workloads? How do we remove that complexity? That's several offerings. So we have on one level VM scale sets, really kind of an Azure construct for deploying sets of VMs, as the name implies. And then you have what our team does, which is Azure Batch, Azure Cycle Cloud, and Microsoft HPC Pack. And then on top of that, you actually have these transformative services, things like Azure Machine Learning, Azure Data Lake, Azure Synapse, Azure Quantum, ML Compute, and others that are really bringing new capabilities to HPC and technical computing environments. So one of our goals is to help you remove that Azure complexity, the technical complexity of running these workloads in either hybrid or cloud only, but also to enable integration with those AI, quantum, and other services, analytics, etc., to really kind of bring your HPC and AI workloads kind of into a new level of value. Excuse me. So the first one we'll talk about is Microsoft HPC Pack. Now, HPC Pack, many of you are probably familiar with this tool, but it is the kind of the oldest of the offerings. It's been around for 16 years, and it is a job scheduler. You can see that there's 3 modes of operation. There's on-premises, hybrid between on-premises and cloud, and then obviously cloud only, Azure only. And so, you know, it was traditionally actually part of Windows at one point, but now supports both Windows and Linux compute nodes. And it's a job scheduler. It has regular kind of batch capabilities, but it also has a service-oriented architecture mode for high-frequency, low-latency scheduling. It is very mature software. And what we have done as part of the Azure team now has been to focus on the hybrid aspect of that. And so running HPC Pack on-premises and then bursting to cloud, to Azure when needed or when appropriate. And we will actually be releasing an update to HPC Pack 2019 shortly, in the next couple weeks, that integrates it with Cycle Cloud to improve the Azure integration further. That integration will bring Spot VM support and Terminate VM support to HPC Pack 2019. At more the Azure workload management side of things, you have 2 kind of primary offerings. We have Azure Batch and Azure Cycle Cloud. So Azure Batch is, simply put, cloud-native job scheduling. It is similar to HPC Pack in that it's a job scheduler, but it is kind of native to Azure, and so it does both the orchestration of the infrastructure as well as the scheduling of jobs onto that. And it's developer-focused. It's API-driven, and it's really meant as the SaaS platform on which partners and users can build their offerings. And then you have Azure Cycle Cloud, the kind of complementary offering. It is traditional cluster kind of management, and it's focused on third-party schedulers. So things like Slurm, PBS Pro, LSF, etc. And the goal there is to enable people to bring the environment that they want to Azure. So if you want to come to Azure and use our job scheduler in Azure Batch or Microsoft HPC Pack, that's great. But if you have an existing environment that you want to build on or that your users want to use, then you have a route to deploy that in Azure as well. So as I mentioned, for Azure Batch, there's 2 aspects of that. There's orchestrating the virtual machines and the infrastructure, and that's batch pools. And simply put, Azure Batch is the easiest way to run at scale in Azure. You can do tens to thousands of VMs. We've had well over 100,000 cores in Azure Batch environments, and it will scale up and scale down, handle errors, can take advantage of low priority and VMs as well as other VM sizes to your application needs. And then once you've orchestrated that infrastructure, then you have the Azure Batch scheduler, which is the job scheduler side, and it's pretty standard. You have your jobs and your tasks, you have some workflow capabilities, some prioritization capabilities, and it will take care of executing your workloads on the infrastructure up and down. And so in addition to the job scheduling, it does do application management. And one thing I want to call there is that it does support Docker container. So containerized workflows are actually very common, and they're run across both Batch and Cycle Cloud. It will auto-scale that infrastructure up and down as your jobs require. And it will provide you analytics and monitoring into what's going on so that you understand the execution of your workloads and can get some metrics and other details. And then most importantly, it is a SaaS platform for cloud enabling your workflows. It does provide API bindings for all the common languages and frameworks, and there are quite a few of our partner offerings are already built on top of Azure Batch. And the nice thing is it really depends on exactly the kind of solution that you're trying to deploy for your users and your customers and whatnot, but you can expose kind of the Azure functionality or not. The goal there is to just Azure enable your capabilities under the hood. So as I mentioned, Azure Cycle Cloud is a complementary offering. And so, excuse me, it does give you instant access to your resources. So you can, in running these HPC environments, you have to define the environment. So somehow you have to say what's in it. Is there a file system or multiple file systems and other services? Is it a standalone NFS filer? Is it something like an Azure NetApp files or HPC cache or Blob or even an IaaS constructed Lustre file system or BGFS, something like that. Maybe you have multiples. We've had customers that had 5 NFS file systems, several MySQL databases, used blob storage, kind of all at the same time. And so you define this environment, and basically you tell Batch and Cycle Cloud go, and they'll deploy that entire environment for you in Azure in minutes. And it does support, Cycle Cloud supports all of Azure's IaaS components. So if it's deployable through a public API in Azure, then Cycle Cloud supports it. And just like Batch, it will do auto-scaling, but as opposed to Batch, which is doing it for its own scheduler, Cycle Cloud supports quite a bit of third-party schedulers and actually has a module that allows you to support your own scheduler. And we'll come to that in just a bit. One of the things we didn't talk about earlier, but if you talk to the analysts like Hyperion and others in the HPC space, they will tell you that customers often cite hybrid and burst as one of their main reasons for wanting to go to cloud. But one of the friction points is cost. Not cost performance, but understanding their costs and feeling like they have control over their costs. And so the fear that they'll leave a 100,000 core cluster running and rack up quite a large bill. And so Cycle Cloud comes, it's meant as an HPC control plane. And so it does give some view into that usage and that's costs, and it's kind of a major focus for us. It does support hybrid workflows. So Batch obviously is for now cloud only in Azure, but because it supports third-party schedulers, a common scenario is for somebody to be running a Slurm cluster on premises or LSF or something else, and then via Cycle Cloud can burst those environments into Azure. And then finally, it focuses on authorization and governance. So it is, again, meant as a management tool. You can almost think of Cycle Cloud as the tool. So if you're the admin that would normally be deploying a cluster and supporting users, quants or scientific researchers or engineers or whoever, then Cycle Cloud is a tool for you to essentially do that definition, deployment, and management and optimization inside of Azure. And so pick your favorite scheduler. As I mentioned, it supports Slurm, Univa Grid Engine, PBS Professional, OpenPBS, Spectrum LSF, Spectrum Symphony, TIBCO Grid Server, and others. But there is also a module in Cycle Cloud called Scalable that is available to Azure enable whatever you need. And so we've had several users and several partners that have used Scalable to add Azure orchestration of infrastructure to their workloads and their offerings. So in Cycle Cloud 8, there was a renewed focus on core HPC operations and Azure platform integration. And so we added quite a few new features since the last year partner airlift. And so we added cloud init support. So that's how when you bring up these VMs, you want them to be usable fully, not just the fact that the machine was started, but you want the software installed, users installed, domain joined, whatever you need. That bootstrapping process now supports cloud init. We made significant performance improvements, so the nodes start up much faster. And as you would imagine, it's an ongoing area of focus. That auto-scaling library, Scalable, and also with that new version of the Scalable library, it did improve both agility and scalability for throughput and tightly coupled jobs. We already talked about scheduler support. It did integrate with Azure Event Grid so that you can get node events, which is very, very kind of deceptively useful for monitoring your environments and responding to changes in them and then optimizing over time. And then there's several other features in there as well. I seem to be missing a slide, sorry. So on Batch, we also added quite a few features as well. Calling out some of the key ones would be Batch now supports private access, basically private Batch accounts, so you can access them through a private endpoint. You no longer need to go over the public internet to access Batch service. We also added support for no public IP pools. What that means is that the VMs that come up are not publicly accessible in any way. They have private IPs only. So these are obviously security-focused features to enable people to run very locked-down batch environments. Very popular in, well, as you imagine, most secure environments, but especially in financial services and a few other industries. We also added support for the service itself. So we've done a significant amount of work on batch itself to make it resilient and scalable and kind of error-proof. And so we've actually done a lot of increased kind of drills and testing to make sure that the service reliability is greatly improved. We want you to know that your offerings can build securely on top of Batch. So what's driving us this year at the moment? Well, our overall objectives are we want to build the most reliable, the most scalable, secure, and transparent HPC platform. And this is obviously not a short-term objective. This is kind of a driving philosophy here. And we want to provide you with the best platform for building and operating your HPC and AI businesses. So, and there's obviously a wide variety of partners in this ecosystem. Everybody from people running these environments themselves to building all kinds of PaaS and SaaS offerings to building solutions that they want their customers to deploy into Azure and hybrid functions. But we want our platform to either remove the technical difficulties there or to give you kind of the capabilities that you need to build your successful HPC and AI businesses. And then recognizing that HPC and AI environments are complex, and a lot of these relationships with our users, both our relationship with you as our partners and your relationship with your customers, are longer term relationships. It's not transactional. You're not, we're not buying a piece of software from us. And so we understand that you need to have a world-class support experience. You need to know that you can turn to us when you have issues. And we also need to know that we can work together to provide that experience to your users so that they don't have, they aren't confused as to who can help them when they run into problems. And so our goal is to build that world-class HPC support experience and earn your trust and your praise. So how does that translate into the short-term priorities in the first half of this year? So for Batch, it means a focus on service fundamentals. So we're going to be, and that'll never leave this slide, no matter when you see me give this presentation. It could be 3 years from now, and you'll still see service fundamentals on there because we're always going to be focused on making the service reliable, scalable, and performant. As long as Evan and Jack and Scott and Klaus and Andrew and everybody keeps increasing the hardware and networking capabilities and storage capabilities that we have, we're going to make sure the service enables you to have access to them. And that's both in the pools and infrastructure level and in the batch scheduler and support for third-party schedulers. We're also going to be focusing on improving live monitoring. So we want you to be able to answer questions such as, what's the progress of my jobs? Do any of them have failed tasks? Just for some details, in Batch, you submit a job and then you assign it tasks. And so the idea there would be kind of the containers of tasks. And then which tasks have just started? Those kinds of more direct queries or insight into what's going on in your workloads or your users' workloads. And then we want to give you improved workload clarity. So that'll be exposing task retries. So if a job does fail or if a task does fail for certain reasons, Batch can retry that for you. But in the past, it wasn't always transparent about when it did. And so jobs can seem to take longer, or there might see some things there. And so while that might result in eventual success, it was definitely an area where we could have been more transparent. And getting back to that philosophy, that's what we're going to be focused on. And then we're going to be focusing on a lot of key features. And this is across both pools and Azure Batch Scheduler, really the entire platform. Some of that will be things like spot VM support, support for tagging VMs, support for things like the ephemeral OS disk feature, as well as managed identity, a pretty key security feature. We're going to give you the ability to update pool nodes to the latest OS version and the ability to spread pool nodes across availability zones. And then at the scheduler level, it's some features that will help you control how tasks execute. So to give you greater control over your workloads and how they're executing, as well as some prioritization features and capabilities around automatically handling errors better, where we kind of fail dependent tasks when the tasks or jobs they depend on have already failed. And then we're always going to work on increasing scalability. And then back to the transparency and kind of clarity, we're going to be improving our logging to give you a better view of the end-to-end interactions. Essentially, every interaction that you, your service, your platforms, etc., have with Batch, we want you to be able to kind of trace through that execution and understand what's going on. For CycleCloud, it's similar. So for CycleCloud, in 8.2, which will be coming very, very soon, there's going to be an update to our OpenPBS/PBS professional support. It will be using that new Scalelib library, or I should say the newest version of the Scalelib library, and so you'll see some significant improvements if anyone's using OpenPBS. We're going to continue working on ISV partnerships and enablement. Nothing specific there, but you know, I think this airlift is kind of showing we view the ecosystem as critical to our success, and so there's kind of a specific focus on enabling you and your offerings through the platform. We'll be adding in public training, publicly available training through Microsoft Learn, MS Learn, and that's going to cover all of HPC, not really just CycleCloud. That's Batch, it's CycleCloud, it's storage, it's kind of advanced HPC topics. It's really the goal there is to help our partners and our users understand our offerings, especially in context, but also to understand kind of the greater HPC space as well. As I mentioned before, job accounting is kind of a key issue for our users, and so we do have support for Slurm job accounting, and we will be doing work to improve and expand on that in CycleCloud. And around the supportability side, so basically helping customers understand what's going on in their environments, and when they do run into an issue, being able to either self-diagnose that problem or to more efficiently get help from us or our partners. And so this gets back to the idea of if you have an environment, an HPC environment, and let's say it's bursting from the customer's environment into Azure, and it happens to be using a commercial scheduler with licensed software with a storage solution, etc. When they have an issue, who do they call? And so trying to help streamline that and work out those agreements to provide that world-class experience to both you and our users and our shared users will be there. Basically what it comes down to is when people run HPC workloads in Azure, we want you, or we want anyone to using it, to understand who is doing what, where, and at what cost. And so moving to have a unified platform with that kind of transparency and that kind of control is really our goal. And so I know we can't do live Q&A, so I'll check for some questions here. But I'll reiterate again just how important kind of our partner success is and how much our focus is on making all these key capabilities in Azure accessible to you, and that'll be kind of the ongoing focus.
Okay, thanks, Rob. Really appreciate that. That was a great overview.
Are there any questions in the thing? I'm trying to check the text. I can answer them live, otherwise we'll just end a few minutes early on my session.
Okay. No, I think at this point, let me share. At this point, we are scheduled to take a 15-minute break. So we're at 6:35 Pacific time. So why don't we come back at about 50 minutes after the hour, wherever you may be. I apologize, I'm kind of judging everything to Pacific time, Redmond time. So let's take a 15-minute break, come back with about 50 minutes after the hour again, and then we'll get going kind of on the next section, which is all about performance tuning with Cormac Garvey. I know from first-hand experience in this morning's session, Cormac will take any extra time we can give him. So we're going to we're kind of conclude this first part a little early, take a 15-minute break, and then we'll get started officially about 10 minutes earlier than the original agenda, and that'll be at 50 minutes, 50 minutes after the hour. So everybody enjoy their break, get some coffee and whatever else, and we'll see everybody in 15 minutes. Thank you.
One thing I forgot to mention before everybody heads out, CycleCloud and Batch and HPC Pack are all free.
Okay.
These are just enablers to use HPC in Azure. And I'll respond to the questions in the thing directly in the chat. Thank you, everyone.
Thanks, Rob. Really appreciate it. That was a fantastic overview. All right, we'll see everybody at 50 after the hour. Thank you. All right. Welcome back, everybody. Hopefully everybody is able to take a good break. Anyways, next is our compute performance tuning with Cormac. So, Cormac, I'm hoping you're there.
I am indeed. Hopefully
Wonderful.
you can hear me.
I can hear you just fine. Sound great.
Actually, let's see. I probably should put on some video. Okay, will I start, Mark? Go ahead.
Yeah, let's get going. Thanks,
All right.
Cormac.
Yeah, great. Thank you, everybody, for attending this session. My name is Cormac Garvey. I work as a HPC Architect in the Azure Global HPC team. The team I'm a part of, we work with customers and partners and who are at various stages on their journey to Azure. We run workshops, do architectural reviews, and co-build architectures with our customers. So the learning objective of this session is how do we get optimal performance running tightly coupled HPC applications on the Azure HPC specialty compute VMs, namely the HB V2, the HC, and the HB series. You know, those who are listening to this talk who have done some performance optimization, it is a never-ending task. It's always a challenge getting that last 5 or 10%. In this particular talk, we're going to focus on some of the key decisions and tasks that you need to do in order to get most of the performance from the Azure HPC specialty compute virtual machines. We're focusing primarily on tightly coupled HPC applications, and so the big difference between this class of applications to, for example, embarrassingly parallel codes is that they, the process need to communicate with each other. And so this is what the Azure HPC specialty SKUs were designed for these particular workloads, primarily because they come with Infiniband. In this session, we're focusing on the Azure HPC compute virtual machines. We're not covering the GPUs. What I will say is that if you have a HPC application which is very much floating point bound, you should certainly consider GPUs. The other point I'd like to make is that within Azure, as you've heard from previous talks, that we have a wide selection of GPUs, and some of those GPUs do support Infiniband. So the very first question that you really need to answer when you're working on optimizing and get optimal performance on a HPC application is selecting the right HPC compute virtual machine for your actual application. So I think it's useful to compare side by side some of the technical specifications of these HPC specialty compute virtual machines. So over on the left hand side we have a number of technical classifications, if you will. And what's highlighted in green is for each of these technical specs on the left-hand side, which of the VMs does best in that category. So if we quickly look at the HB 120 V2, it has the largest number of cores per VM. It has the maximum amount, or the largest floating point performance per VM. You can get up to 4 teraflops. You can also run the largest MPI jobs with this particular virtual machine, up to 36,000 cores. It has the largest memory. It has the best memory bandwidth, up to 3. And it has the latest generation of the Infiniband hardware available in Azure based on the HDR, which is 200 gigabits per second and close to a microsecond of latency. It is also very strong with the local scratch space, the local SSDs. It's the only HPC VM which supports NVMe Direct. And also, if you're running an IO-bound application and you're satisfying attaching disks, you can attach the most amount of managed disks to that particular VM. The HC44, where it is strong, is it has the highest clock the highest base clock frequency of these particular virtual machines. Also, just by the fact it is the only one that actually supports AVX 512, so on a per core basis, it can actually give you the most amount of flops, up to 32 flops per core. It is maybe the easiest virtual machine to actually program and to run code, primarily due to the fact that it has the smallest number of Pneuma domains, and generally it's just easier to work with. The big advantage with the HB60 is that it is the cheapest virtual machine of the HPC specialty compute VMs, and so there is a set of workloads which are suitable for that particular VM. So with that knowledge and with that comparison of this technical specifications, we can kind of map the application performance characteristics to each of these virtual machines. So if we consider first the HC44, which is based on the Intel Skylake processor, so applications which are maybe of a serial nature, running on a one core, or for example, it's an application which has a very expensive license per core. This may be a good choice for that particular workload. Also, the Intel processors have been out a lot longer than the AMD process, and you could make the argument that it maybe has a more mature ecosystem, and just by the fact that it has only 2 Pneuma domains, it's easier to program and to run jobs on this particular virtual machine. The HB V2, it's strong if you have a parallel code which you require scaling to a high level. It has the best of class of Infiniband, which helps with scaling codes. Also, the fact is that if your application is very much floating point bound and you can leverage the AVX2, you'll get the most amount of flops with this particular virtual machine. It's also strong in regards to storage, scratch and manage this, as we talked about. The sweet spot for the HB60 is if you have a code which it isn't really floating point bound, it is memory bound, and it doesn't run on a particularly large number of cores. The HB60 would be the most cost-effective VM to run in that case. So switching topics to process and thread pinning. In this section, we're going to be talking about manually pinning process and threads on your VM as opposed to the operating system choosing where the process and threads run. And so why would we do that? Well, the primary reason is that really helps maximize the performance. We maximize the performance by manually pinning the process and threads. We maximize the memory bandwidth by guaranteeing that we utilize all of the memory channels. Also, if we're pinning process and threads, we're going to pin them in places where there's going to be optimal communication, where there's going to be a lower latency, higher communication throughput, and that also helps performance. And the fact that we're pinning in the process and threads, we're going to get better core utilization. There's less chance that you're going to have maybe a situation of 2 processes running on a single core. And the fact that we're manually pinning process and threads, the OS doesn't need to be concerned with that, and so it does reduce the OS overhead. Over on the right-hand side, we see the HB60 Pneuma topology. This particular processor has 15 Pneuma domains, and each of the Pneuma domains has 4 cores. And in this particular case, each of these Pneuma domains maps to what AMD calls the AMD Core Complex, the CCX, and you could kind of consider each of these Pneuma domains to have a single memory channel. So the way to maximize the utilization of the memory channels would be to pin process in a round-robin fashion amongst all of these Pneuma domains, so to make sure that you get usage of each memory channel, which will maximize the memory bandwidth. And by spreading the cores over these Pneuma domains, you're going to get better core utilization. The other advantage, of course, by manually pinning process and threads is that if you're running a similar job multiple times, you're going to get more consistent results, because everything is the same. You're pinning process in threads in the same location every time you run it, as opposed to maybe some random behavior when the OS actually decides where it wants to run those processes and threads. So in the previous slide, we talked about why we pin process and threads. Now we want to just talk a little bit about where we pin these processes and threads. So in order to do that, we need to have a clear understanding of the process Pneuma topology in order to make that decision. So there are some useful tools which will help you give you the process Pneuma topology. The first one I'll talk about is the LSCPU, which is a pretty basic tool. It'll give you the number of Pneuma domains on your virtual machine, and also which core IDs are associated with which Pneuma domain. From the hardware lock package, you can use a tool LSTopo no graphics, or LSTopo, and that will give you some additional information, not only the number of Pneuma domains and with the core IDs where they're located, but also where the L3 cache is located and where NICs are located on that virtual machine. You get the most detailed information from a tool like the Intel Memory Latency Checker. This particular tool gives you the same information the previous tools that I mentioned give you, but it also, this tool actually runs latency, and it can run latency and bandwidth benchmarks between each of the Pneuma domains, and you can kind of create images like on the right-hand side. So this is the sort of information you get from the Intel Memory Latency Checker for the HP 120 V2, and you can clearly see the Pneuma topology here. Now, there are some situations running some codes where, and we've seen this with some ISV codes, where they run well with Intel processors, but then when you run them on, for example, a HP V2, which has many Pneuma domains, the performance drops off. And after working with some ISVs on this issue, we have found that some codes, they like to, at a very low level, manage the number of Pneuma domains, control what sections of what sort of work is to be done in each Pneuma domain, and managing which process and threads run on each of these Pneuma domains. And even though these particular applications, they recognize 30 Pneuma domains, there's a tremendous amount of overhead with this management, and it kills performance. So one solution to this is, from a software perspective, reduce the number of Pneuma domains to number of Pneuma groups. And the sweet number of Pneuma groups for the HP V2 is 8. And you can see that clearly if we take a look at the Pneuma latency map on the right-hand side. The dark green boxes represent each of the Pneuma groups, and these boxes have the lowest latency, and each box is composed of 4 Pneuma nodes, and together it represents a Pneuma group. So by using doing this mapping, we reduce the overhead, because the software only has to deal with 8 Pneuma groups as opposed to many Pneuma domains, and also we can pin the processes in optimal locations based on this information, and you can get some significant improvements in performance. Also like to make a comment on, when we're thinking about performance, it's usually best to think in terms of the actual job performance, or the overall VM performance, as opposed to, or for example, the aggregate throughput, instead of just considering just the performance on a per core basis. So for example, the HP V2 has 120 cores. There are situations that if you utilize all 120 cores, your code may not perform as well. It sometimes performs better if you utilize less of the cores. And the reason for that is those type of codes can be memory bandwidth bound. And if you're running less process on the VM, then each process has more of a memory bandwidth, and the performance improves. And the same argument in regards to running, you may get better aggregate throughput if you run multiple jobs on one of these processes which have a lot of cores, and get better aggregate throughput that way. So key observations from the pinning and recommendations is understand the Pneuma topology, how many Pneuma domains you have, which core IDs are in which Pneuma domain, and then pin the processing threads in a round-robin fashion amongst the Pneuma domains. So in the case of the HB120v2, which has 30 Pneuma domains, you might do experiments running 30 processes, 60 processes, 90 processes, 120 processes on that VM, which correspond to 1, 2, 3, and 4 processes per Pneuma domain. And you kind of figure out which number of processes works best for your actual workload. In the case of hybrid parallel applications, the key there is to kind of group the processing threads in the same Pneuma domain to keeping the data close to the L3 cache. So in the next section, we're going to talk a little bit about some compiler and numerical library considerations. But before we get into that topic, I just want to say a few words on some recommendations on what HPC image to use. So in this particular case, we are talking about tightly coupled HPC applications. So the IB interface needs to be available. And so I think a good starting place for anyone running these types of codes is to utilize the CentOS HPC marketplace image. The primary reason to use that particular image is that it comes, the drivers come pre-installed. So the Infiniband drivers come pre-installed. The Infiniband will be working out of the box. It also has the convenience of having a number of the popular MPI libraries pre-installed on that particular image. It sets the appropriate limits so you don't get the inconvenient errors from running a tightly coupled MPI code not having sufficient or high enough limits for the locked memory, for example. It also comes pre-installed with some numerical libraries. So the AMD optimized CPU library and the Intel MKL are pre-installed in this image. For customers who need to or want to create a custom image, a good place to start would be these two GitHub repositories. The AZ HPC images, this is really a reference implementation of the actual CentOS HPC marketplace image. So all of the scripts that create that marketplace image, you can get access in this repository. And the Azure HPC, which is an end-to-end deployment framework, also has some scripts which can complement the AZ HPC images repository. And between those two, I think you'd have a good start to creating a custom image. Also, there are a number of services in Azure which help with the custom image building process. The Azure Image Builder, which is a wrapper for Packer. You basically pass in a Packer template and it can generate an image for you. And then to manage and control access and to actually use the images and store the images, you can utilize the Azure Shared Image Gallery. So just some comments now on some compilers. So generally, if you're building, say, for example, an open source code the very first time or any application in Azure, it's usually, if that particular application recommends a particular compiler and compiler flags, it's maybe good to go with that initially. It's always best to get something working before you really start working on some of the optimizations. And once you have it working, then you can do some further tuning. But overall, on the Azure HPC specialty SKUs, the Intel compilers work well, not only on the Intel process, but also on the AMD-based virtual machines. Some specific comments for the HB-V2 and the HB series. Besides the Intel compilers, GCC compilers work very well. The only point I would make here is use a fairly new version, so it will generate tuned instructions for the AMD processors. Also, AMD has a compiler that it develops, the AMD optimized C and C++ compiler. Some comments on whether you should or should not enable AVX2. In general, enabling AVX can hurt performance. So just be careful with AVX. If you know your code does well with AVX2 or is very much floating point bound, then certainly go ahead and enable that. Similar comments for the HC virtual machine. Intel compilers obviously work well. This is an Intel-based processor. Generally, any of the GC compilers work well. The HC virtual machine is the only one that does support AVX 512, but similar comments to the AVX2. I wouldn't necessarily enable AVX 512 for all codes. If it's floating point bound and you do know it's going to work well with AVX 512, then by all means enable it. The options here that I'm showing for both cases here are for the Intel compiler, enabling AVX2 and AVX 512 with Intel compilers. And as we know, compilers, there's a lot of options, and by playing with the other sort of options, you may improve your performance by a couple of percent. So a lot of HPC applications, they have a lot of external dependencies, and a lot of them have dependencies on some tuned libraries, specifically the BLAS library, which is basic linear algebra subprograms, which is a standard for doing computations like matrix multiply, matrix vector operations, and vector operations. Also, another library that is that applications expect the tuned version is the LAPEC library, which is a standard library for doing linear algebra type operations, like for example, solving a linear set of equations. And today the de facto standard for FFTs is the FFTWs from MIT. Fortunately, as I mentioned earlier on, we do have tuned versions of all of these libraries on the CentOS HPC Marketplace image. A lot of these tuned libraries are resolved from the AMD optimized CPU library in the case of the HB V2 and the HB series. In the case of the Intel process, like for example the HC series, a lot of these libraries are resolved from the Intel MKL library. So in the pinning section, we talked about why we manually pin processes and threads, and we talked about understanding the topology where to pin those processes and threads. Here we're going to cover a little bit about how we actually do that pinning and how we actually pin processes in a round-robin fashion amongst the Pneuma nodes. But first, a couple of comments on MPI and MPI in general on the latest generation of the Azure HPC specialty compute virtual machines. So today, it really has a very much of a bare metal feeling because of the single rank IO virtualization of the PCI Express. So this means that we can support all popular MPIs now on the HPC, especially compute VMs. Similar comments to the compiler when you're building a code. Even though MPI is a standard, some codes may, for example, test or prefer a particular MPI. To get a code working, if I would suggest go with those recommendations first. If you have flexibility on which MPI you can select, overall we recommend that you use HPCX. This gives the best overall performance on the Azure HPC compute VMs. It is highly optimized and takes advantage of the Mellanox optimization in their hardware and their software optimizations. So now some specific flags for the HPCX and OpenMPI MPI libraries to pin process and threads in round-robin fashion amongst the Pneuma domains. I want to focus more on the -- map by option. I'm using a very generic version of this option, and you can see I have a variable, the number process per Pneuma. So in the case of HB V2, which has 30 Pneuma nodes, and each Pneuma node has 4 cores per Pneuma node. This value would either be 1, 2, 3, and 4, depending on how many cores you want in each Pneuma domain. If you were just using an MPI only code and it's not hybrid parallel, then you would set the PE is equal to 1. So for the variable number of threads per process would be 1. If you were running a hybrid parallel code, then the PE would be equal to either 1, 2, 3, or 4, depending on how many threads you want in each Pneuma domain. And always with any sort of MPI options, I think it's always a good idea to specify some option where you can verify that your pinning is correct. So in this particular case, the dash report bindings, when your job completes, you can kind of go in and check and see where your processes were actually pinned and to verify where they pinned it correctly in a round-robin fashion amongst the Pneuma domains. If your application is doing a lot of collective communication, then you can enable some additional options here to do more aggressive hardware offloading. Similar comments here for the Intel MPI. The Intel MPI interfaces with the Infiniband fabric through the libfabric API. The preferred provider is MLX. This will take advantage of the Mellanox hardware, the optimization of the Mellanox hardware and software. The other provider that you could choose if there were you found some issues with the MLX would be the Verbs provider. Both of those will use Infiniband. And then the other options there basically allow you to get information about your pinning when your job's complete. And by specifying Pneuma here, we're basically saying pin your process and threads in a round-robin fashion amongst the Pneuma domains. Similar comments regarding collective communication. If you're using Intel MPI, you can set an additional flag here, and if you're using the MLX, you can get additional hardware offloading, which will help with collective communication. MPI has a lot of options, but be careful with some of these advanced options. They can also hurt performance. Before considering some of these advanced options, I think it's good to do an MPI profile and understand exactly the communication mechanism in your application. Is it point to point? Is it collective? How many messages? What are the size of the messages, etc. And then you can kind of figure out, sort of dive in and figure out which of these options may help with your performance. So far in this particular talk, we kind of talked a lot about a couple of tips for creating an optimized, a tightly coupled HPC application. We talked about some tips about running that code optimally and getting most of the performance out of the Azure HPC specialty VMs. But before you hit that submit button and schedule that job, we really recommend that you do some pre-run preparation. This is a little additional work, but I think in the long run it'll pay dividends and cause you to have potentially less frustration. So the first point is health checks. Within Azure, before a customer gets a virtual machine, we internally do a lot of checking to prevent a customer from getting an unhealthy virtual machine. But we're not perfect. Sometimes that happens. We're continually improving that process to make it better. But where we are today, especially if you're running a tightly coupled MPI code, a single VM can cause a hard failure. So we do recommend you do some health checks. So what sort of health checks should you do? The first one is check Infiniband, any sort of ping pong or all reduce that measures the latency and bandwidth, and you can compare that with the expected values based on the Infiniband fabric that you're using. Also, the CentOS HPC images do also come preloaded with the Mellanox cluster kit, which is also a tool which can verify that the Infiniband fabric is working correctly. Other tests to do would be check the memory. Any type of stream benchmark will be able to kind of tell you if you have bad memory or not. And then if your particular HPC code is I/O bound and you configure, say, a parallel file system, it's also good before running that test to run your favorite synthetic benchmarking code, measure the throughput and IOPS, and verify that it's performing correctly. If you suspect any issue with the floating point performance, running a high-performance linpack is always a good idea, and will quickly tell you if everything is functioning properly or if you have an unhealthy virtual machine. Fortunately, a lot of these health checks are contained in the Azure HPC repository. In the apps directory, there is a health check directory which contains a number of these health checks, so you could use that as a starting point. The final point I want to make is in regards to application scaling performance. If you don't understand how your application scales, I think it's a good idea to do a parallel scaling study for a number of different VMs. Calculate the parallel speed up, and maybe more importantly, calculate the parallel efficiency. That way, for your particular HPC application and model, you can pick an optimal number of virtual machines for that job, which will give you the performance that you want, and also in a cost-effective manner. With that, I'm going to stop there. Folks on the call, if there are any sort of questions, please submit them to the Q&A. We'll do our best to answer those questions. And with that, Mark, I'll hand my time back to you.
Okay, thanks, Cormac.
Sure.
Really appreciate it.
Yeah, thank you.
Okay, so now we have our friends from NVIDIA up, and I know we're running a few minutes early, so I'm hoping this team is available. We got the NVIDIA team on. I guess I'll take that as a no. So Michelle, do we know where those folks are?
Hi, Mark. They're on. Let me just grab really quickly here. I just shouted them. 1 second.
Okay.
We're here.
Okay. Great, guys.
Okay.
Hi, Dave. How are you?
Hey there. How's it going?
Doing well.
Let me start sharing my slides here.
Okay, perfect. Yeah, sorry, we're running a little early, so appreciate you guys being flexible, and that way we can just get through everything and probably finish up a few minutes early. So,
yeah, let me start sharing here. Let's see. Okay, there it is. Let me know when you can see this.
Yep, I can see it just fine. Thanks, Dave.
Okay, great. All right. Well, as was probably said in the introduction, I'm Dave Salvatore, and I am with NVIDIA's Accelerated Computing Group. And I'm here with my colleague tonight, Dion Harris, and we're going to talk to you about the NVIDIA platform and how to make the most of it on the Azure Cloud platform. We do a lot of collaborating with Azure, and together we deliver GPU acceleration in some of its best forms on the Azure platform. So with that brief intro, I'm going to go ahead and get going. Okay, so one of the things we'd like to talk about a little bit is, what's behind the shift to GPU computing? There's been a lot of discussion about this, a lot of news coverage about it, etc. And so, what has propelled data centers to want to adopt more GPUs? And the answer, in short, is the workloads. And I'll talk more about that, but it's the workloads are one of the major drivers, but the other driver has been what we were calling the end of Moore's Law. And recall that Moore's Law has sort of been this gospel commandment in our industry that says you get 2x the number of transistors about every 18 months or so, with which architects can do all sorts of wonderful things to give us more performance. And what we've seen is that curve has really started to roll off over the last several years. And so now, year over year, we're typically getting on the order of 5 or 10% incremental performance from new CPUs. Meanwhile, the GPU performance sort of slope, as you can see here in our slide, is significantly steeper. And that's coming through a number of things. It's coming through a combination of architectural innovation, things like our Tensor Core technology, for instance, which we debuted in our Volta architecture. And it's also coming, oops, it's got a timer on it, there we go. And then it's also coming from just relentless software optimization. In other words, we have just a ton of work that we do around software. And you'll hear me talk quite a bit about the importance of software and software enabling an optimization for the ecosystem to really make GPUs be all that they can be. And I'll be talking more about that as I move through my talk. But, so what we've been able to do is really kind of put that growth curve on a much more aggressive slope to deliver more performance to the industry at a time when it's desperately needed, because workloads and data sets are just growing exponentially. And the result of that is that you need a lot of computation to be able to get through those data, those workloads, those networks in a timely way. The other thing, of course, is that, industries of all kinds have been accumulating data over the years, through a combination of sensors, data analytics, what have you. Many companies across many industries now have these just massive lakes of data, and have used things like data analytics and what we call sort of traditional machine learning to extract insight from those data. And so, we just sort of provide a few examples here where we're seeing data science making all kinds of impact. If you look at financial services and things like fraud detection, for instance, where we've seen companies like American Express and PayPal using our technology to accelerate how they do their fraud detection to get better hit rates and implement more robust solutions that they can run in real time, right? It can be things like retail, for things like supply chain management, as an example. Telecom with things like 5G. Healthcare, of course, is a big one, and you'll hear Dion talk more about that one in a few minutes, because as it relates to high-performance computing, which is, I know, what this audience is primarily interested in, we've done and been, well, I should say we've been part of some phenomenal work in the healthcare research field, and I won't steal too much of Dion's thunder there, but he'll tell you more about that. So suffice to say, that data science is really, again, is really making an impact across multiple industries. And so, through a combination of factors that I've just sort of enumerated. In terms of, as you sort of make your way into AI and deep learning in particular, though, we start to see, even more impact happening, and so that can be, again, from anywhere from things like healthcare to infrastructure, and to things like IoT. And these last two examples have to do with basically preventative maintenance and predictive maintenance as a way to get ahead of things before they actually break or go wrong and fix them to reduce costs, right? Most importantly, on this slide at least, one could say that some work we've done with the Ohio State University in Ohio, obviously, is around radiologists being able to detect a stroke in patients who come in presenting stroke-like symptoms. And in the case of stroke, every minute matters, right? And that ability to basically nail with better than 80% accuracy whether or not there may be signs of stroke damage to a human brain can be, a difference between potentially even life and death. So another factor that's driving this this migration towards GPUs and accelerated computing in the data center has to do with the fact that while AI is this amazing thing, it's also deep learning in particular is a relatively nascent form of AI. AI has actually been around really since really the late 1940s, going all the way back to Alan Turing, as a matter of fact. With that said, the techniques around deep learning and building deeper neural networks with many layers is a relatively recent phenomenon that's only been with us for just under a decade. And so in that decade, there's been a phenomenal amount of innovation made possible in large part by GPU acceleration, because a lot of what these networks do is only made possible because of the computational horsepower that we bring to the table, right? But you see, there's a real variety here of networks. It's not just any one kind of network. There's a whole variety of them, and more are being invented, as we move through time. And more importantly, many cutting-edge usage models around things like natural language processing, as an example, and real-time conversational AI require multiple networks or an ensemble of networks. And that has to run in real time. So in other words, you don't just have to get the right answer, you have to get the right answer right now, right? So you've got all these factors combining to drive a need for acceleration in the data center that that is something that we at NVIDIA have been very proud to work and deliver to the market. Now, one thing that I want to talk about here when we talk about our platform, and that's an important concept for us, is that a lot of people associate NVIDIA with GPUs and gaming, and that is certainly a proud part of our history and our DNA. It's an area where we continue to innovate and bring new products to market for gamers all around the world, myself included. But with that said, when you look at our total platform, what you'll notice is that the hardware pieces of our platform sit at what we'll call the foundation of the house. But that the rest of this house that you see built upon it is all software. And that's a really important thing to know about NVIDIA, is that NVIDIA, we actually have twice as many software engineers as we do hardware engineers, and that is very much on purpose. That is because we understand the importance of ecosystem enabling and the importance of using great software to unlock all of the potential of great hardware. And so what you see is that, we accelerate every AI framework that's out there. We accelerate hundreds of HPC applications. I think we're up above 700 HPC applications we accelerate today, with more being added all the time. But in addition to that, we also have things like pre-trained networks, and I'll talk more about this probably on the next slide. Oh, excuse me, I've got plenty. Popping up there. There we go. And so a whole host of components to our platform are in fact software. That includes things like application frameworks, like I mentioned just a minute ago, natural language processing. We have a framework around that called Jarvis. It's an example for conversational AI. Recommender systems, we have one called Merlin. For autonomous vehicles, we have Drive, etc. So we have some of these industry-specific application frameworks which make it possible for developers to take advantage that much more quickly of the acceleration that GPUs make possible. Right? And the other interesting way I want to just sort of show you a look at the software is, that our software stack is also end-to-end. And this is a bit, obviously, is more focused on AI, because that's sort of my area of focus on the team. Deanna is going to talk to you much more about the HPC side of the house, because that's his area of focus. The interesting thing, and Deanna will cover this more, is that those two areas have really come together. Because as it turns out, another thing that AI is really good at accelerating is HPC. And I don't want to steal any more than Deanna's thunder, so I'll leave that right there. But as it relates to AI, what you see here is that you have the ability to start with our development environment as you do things like getting data ready, basically doing what we call pre-processing, data augmentation, what have you, to bring the data in, ingest it into networks, then train those networks to get them ready for deployment, optimize them and compile them using TensorRT, which is our runtime compiler, and then ultimately deploying them using something like our Triton inference serving software. And all of this, of course, runs wonderfully on the Azure platform. And so, again, not only do we deliver sort of this broad swath of software, but we think very much in terms of workflows and sort of end-to-end solutions, and not just, one step of the process or one particular application. We're not only sort of, broad, but we're also deep. Right? And one of the ways we do that is through our NGC container repository. This is available at ngc.nvidia.com, where we make available for free a huge amount of software, almost all of which is containerized. It's pre-configured, pre-optimized, and ready to rock. And so by using containers, it allows developers to focus on the real work they're wanting to solve for, and not having to do things like configure, drivers and libraries and this, that, and the other. That's all done for them ahead of time using containers. In addition, we also have pre-trained models where developers are able to take that model and then fine-tune it using their own data sets. And we even have some development tools around that called a transfer learning toolkit that allows you to do that. We have application frameworks, which I've touched on already. We also make available things like Helm charts for machine learning and inference. And then collections, which is similar to kind of the end-to-end workflow framework idea. And these are containers that are sort of being put together that make logical sense for specific development workflows. And those are relatively new, new addition to NGC, and they're something we continue to work on and bring to market as we figure out which are the right ones to put together to help people, again, unlock more of that potential of our platform. And of course, all of this is available everywhere, whether that's in the cloud, on-prem, hybrid cloud, and edge. So in other words, it can be run anywhere and everywhere that you have your acceleration as part of your data center infrastructure. So what does that get you? I've talked a lot about platform, I've talked a lot about software. Well, what it actually gets you is world-leading performance. So what we're showing here is some data from the most recent round of MLPerf. This is from 0.7. These are the training results. And what we delivered to the industry was the industry's fastest shipping training performance across the board. You'll notice here there are a number of workloads. I believe it's 7 or 8 workloads in this benchmark. We were the only company to submit for all of them, and we were, of course, the only company to win all of them among shipping commercially available products. And so, not only do we have, the performance leadership, but we have it across the board. So it gets back to having both breadth and depth that really makes our platform ideal because of the wide variety of things it can accelerate very well. In a similar vein, with MLPerf with 0.7 on the inference side of the house, we also deliver leadership performance. So when you think about the two major operations of AI, one being training, the other being inference, we deliver leadership performance across the board and end-to-end, right? So, when you think about a platform of choice, from not only, the wide variety of things we can run, the versatility, but also the performance, ours is a pretty tough platform to beat. The great thing, of course, as well, when we talk about the GPUs in the cloud, and this was touched on earlier, so I won't dive too much into this, but they've got a whole array of instances available for you on Azure, right? There's at least 8 that are available today. The 2 that I'm going to just quickly touch on are on the far left-hand side of the slide, with the one based on A100, the NDR V4, as well as the NCAS T4 V3. These are both our current generation products. We're particularly excited about the work we've done together with Azure to bring the A100 instance to market. The Azure team has done a phenomenal job building an instance that not only brings our great GPUs onto their cloud platform, but they've put a lot of really robust infrastructure around it, most notably the networking and the storage. So when you think about wanting to use the A100 GPU for really heavy-duty compute, and you need scaling out of that, in addition to having maybe just run 8, or if you want to run even more, string together several instances, the Azure platform, with the infrastructure they put around the A100, is really going to be just a phenomenal platform for you in the cloud. The T4 as well is a terrific product, mostly focused around things like inference and cloud gaming. Very versatile processor, and again, many available in the cloud from Azure. And then, of course, we have the others in market, which represent some of the technologies that we've built over the years, all of which are terrific. I would, of course, I'm particularly proud of the work we've done on A100. So if I had to advocate one, that would be the one I point you toward. So again, a wide variety of instances of our technology available through Azure, and again, the Azure guys have done a great job in terms of the infrastructure that they build around our GPUs in their data centers. In addition to that, there's also the Azure Stack family related to edge solutions, right? So you have, Stack Edge, you have Stack HCI, and of course Stack Hub. These are also currently built on T4 and then our V100 technology, which is based on our Volta architecture. These are all terrific solutions for those customers that are looking to build hybrid applications or hybrid infrastructure for whatever reason that may be. It could have to do with regulations around the types of data you work with. It could have to do with significant concern around data privacy, GDPR. There's any number of reasons why you might want to be doing a hybrid implementation where maybe data has to live in a certain specific part of the world and needs to be primarily localized there. These 3 platforms give you that flexibility to, again, build the infrastructure you want to build where the right amount of infrastructure for you will live on-prem in your own data center, some amount at the edge, and then perhaps you're bursting to cloud, as an example. So again, just another degree of freedom that you get in terms of using our GPUs in the Azure platform. And one last thing I wanted to talk and touch on is that our software, in addition to all the talk I've had about software, sort of in our own context, runs wonderfully on the Azure platform, right? The other place we've done a lot of collaboration with Microsoft and the Azure team is around integrating our software technologies into the Azure software stacks. In particular, Azure ML is another place where we've done a lot of work to make it easier to use our GPUs and to use GPU acceleration. And things like our TensorRT inference runtime and optimizer, as well as our Triton inference server, also have been integrated so that they're easier to use, easier to bring up, and get you deployed with a solution running that can get you faster time to insight, faster time to value, right? And again, all this, of course, available across all the instances of GPUs that Azure makes available. Okay, so with that, that is my portion of the talk. I'm now going to hand this over to my colleague Dion, who's going to talk about the HPC side of the house. So Dion, it's all yours.
Thank you very much, Dave. I will just share this here so we can get going. And again, thank you guys for joining us this this evening or morning or afternoon, wherever you are in the world. Again, we're excited to talk to you about all the great work that not we're doing, but really the HPC community is doing around the platform. And that's inclusive of our Microsoft partners and a lot of you folks on the phone. So again, lots to cover, so I'll go ahead and get started. When we look at sort of what's going on in HPC and just scientific computing as a whole, I think it's really interesting that no one would agree with the notion that the data is growing. It is exploding by leaps and bounds. When you look at just the data, that's been created in the last 2 years, they say that basically accounts for over 90% of the data that exists. So just in the last 2 years, right? And so that's continuing to explode. You see that we're projecting to be up in the hundreds of zettabytes in the next few years. And when you look at sort of what's generating a lot of that data, in addition to user-generated content and all the various internet and hyperscale use cases, a lot of the scientific simulations themselves are generating data. So, for example, if you look at just the COVID simulation, for example, so simulating the COVID capsid, it created a graph analytics database that was over 390 terabytes in size. Similarly, if you look at the square kilometer array, again, canvassing the sky in real time, capturing images and processing that data across, thousands of satellite collection instruments, that will generate over 16 terabytes per second. And then also we recently did some work, I should say roughly last year with NASA, capturing their database and helping them simulate the Mars lander. And again, just simulating the first 3 phases of that landing generated over 550 terabytes of data. So again, this is really forcing data centers to think differently about how they build, architect, and think about their solutions. And then, of course, with as Dave was alluding to earlier, AI is growing and it's driving the need for even more data, right? So that's one of the things about AI is that it thrives and lives and breathes off data in order to train models and to build the accuracy required. And of course, being that HPC is generating and creating all this data, there's a perfect marriage that we see, and we'll talk to that a little bit later. But again, I think everyone would agree that this is forcing us to think differently about how HPC builds, consumes, and creates overall HPC infrastructures. And the way that this is sort of manifesting itself, it's really, like I said, creating an expanding universe of scientific computing. Whereas before you used to say, okay, all I need is a large piece of metal that I'm going to run my FP64 double precision codes on, and I can churn that out and have maybe an analytics node on the side, and that would get you a large majority of what you needed. But what we're seeing now, you not only need something for simulation, you need to be able to visualize that data. You need to have data analytics at the database and at the edge in order to understand and process and filter a lot of data coming in off of those sensors. You need to have, streaming edge devices to capture and transmit information across the network to the storage, back to that mainframe supercomputer you have back. So all of these elements are becoming very tightly wound and coupled and interdependent on each other. And then of course you have cloud, right? That's now another layer in how HPC is really building and growing by having that burstability, having that flexibility in the infrastructure to help accommodate for some of those new workloads. And the way that NVIDIA has approached this, and I think Dave hit on it, very, very well in the setup, is that, we're looking at it holistically. And I think this has been our approach from the beginning, is that, really requires, in our minds, 4 key areas of innovation, if you will. So the first one is, of course, you got to have a great GPU, right? You got to have something that's going to give you all the flops and tops and acceleration that you need to get out of a fully optimized accelerated solution. Of course, that needs to work, very tightly integrated with the CPU and the DPU, data processing unit, something that we really are driving a lot of value through the acquisition of Mellanox. And again, having those work in concert is really key to get the optimal performance out of your computing. But of course, it's much more than computing, right? It really requires full stack optimization, and that's across the networking, right? I've heard a lot of discussion around how the IB components can create a lot of value, right? Because once you start stringing together these compute nodes across, kilometers of data centers, you really need a very strong and powerful networking stack to help enable that communication across those nodes. Of course, compute has to be powerful, and then the acceleration built within the application itself, again, needs to be very, very well thought. And then all of this needs to have a solid development foundation and platform. So that's all the various tools, the profilers, the compilers. And so you need a very well finely tuned stack that can integrate all of these elements. And then by definition, this third column to the right is basically data center scale. And by definition, HPC is a data center problem. It's not a single node problem. It's not a single GPU problem. So when you hear a lot of sort of comparisons and bake-offs that'll give you a flops per GPU type of evaluation, it doesn't get at the heart of the problem, especially when you're referring to HPC, right? So you really need to think at a data center scale. And that was one of the main reasons we looked at acquiring a company like Mellanox to really start to tie together all these elements across storage, across compute, across networking, even power and cooling, understanding how all those elements come together to really deliver a fully data center scaled solution. And then last but not least, it's really about the architecture and the ecosystem. And that's where we leverage our install base, we leverage our developers to then create more performance, which then builds more value into the platform. And that's why we talk so much about software, because we really do believe that having that reinforcement mechanism of investing in the software development efforts with our developers, with our partners, that really generates the value for our customers at the end. And so all of that really culminates into what we call our HGX AI supercomputing platform. And in the past, you may have heard of this referred to as just the GPU baseboard. And that was really sort of a form factor which we would sell into various systems, including cloud providers. And again, I think the key thing here is that we recognize that you can't just optimize at a GPU level. You need to have a full stack and integration across all of those elements. And the great thing about what we're able to see in these Azure instances, and again, I think they mentioned them, the NDV2 and the NDV4 in particular, is that we do have full integration across the InfiniBand network with the 200 gigs, in a bandwidth connectivity across the node. We do have all the software stacks that's enabled by Magnum IO and the CUDA-X libraries to facilitate, again, that end-to-end integration. And then, of course, we have, our software SDKs, which allow you to build applications on top of that platform, right? And one of those in particular is the HPC SDK. And the reason why this one is so compelling, again, of course, all the other ones you'll need for AI, Rapids development, Clara, again, for life sciences. We'll talk about some of that in a second, Omniverse for visualization. But the HPC SDK is very key in that it's really what an HPC developer is going to lean on, right? It's the compilers, it's the profilers, it's the MoFed stack that's being integrated for networking. So it's giving all you need to really start building out your HPC solution in a single SDK, along with, again, all the integrations across the overall platform. And so this is key in that we have this full stack implemented in the Azure Azure cloud. And this is just an example. One of the things I really was impressed with working with the Microsoft team, and in fact, I was engaged with some of our dev techs over a weekend a couple years ago as we were rolling out the NDV2 instance. And we don't just say, we're going to give us a benchmark to see how it performs. We're going to throw HPL on there and call it a day. We're really adamant about trying to understand how will applications perform on this system? How will applications scale on this system? In other words, if you can rent a supercomputer in the cloud, we want to understand and see how it behaves truly as one performing coherent unit. And so in this case, we basically took LAMMPS, which is a molecular dynamics code, and this is a Lennard-Jones data set, which is looking at roughly about 2 million atoms per GPU. And the thing about this, although this is a very pretty marketing slide and it looks like a very straight line, if you plotted the dots, it looked exactly like this. In fact, when we got the data back, we weren't sure that it was exactly quite right, because you always expect it to be, you know, a little sublinear. But in this case, we were achieving, you know, almost near linear scaling across hundreds of GPUs in the cloud. So it really enables customers to go in and rent a supercomputer for an hour, right? So that's a very unique offering. And again, what we also saw is that in addition to being able to run roughly 2 million atoms per GPU, we had the headroom to run up to 8 million. So we were able to really push the bounds of that. And so, you know, it's just one of those things just to show how powerful the solution is when it's fully deployed in the wild. And again, you know, when we talk about being able to do this work across multiple domains, multiple workloads, NVIDIA prides itself in being leaders across all of those domains. So having a single platform where you can say, I have the best simulation platform, I have the best AI platform, data analytics, you know, is definitely setting new marks and thresholds, and of course having the most energy efficiency. So when I look at some of these elements here on the far left, when we're describing HPC, we took a basket of apps, real applications, measure those over time, and what we're seeing is that the application itself gets better over time, right? So if you're looking at this bar on the far left, years 2017 to 2019, those are based on the V100 platform, right? That's something like the NV2R instance. And so what we're able to see is that performance, even though you had the same underlying hardware, still got better over time because of the software improvements on our side, the application owners and developers owning that and building in more parallel elements within their code, leveraging more parts of the actual GPU itself. And then, of course, you see, and with the A100, we get another big leap. But the great thing is, as we continue to move forward in that platform, you're going to see more incremental improvements across the A100 platform as well. And then, as Dave alluded to, number one in ML Perf and AI, and I think that's fairly well explained. But also, when you look at our performance across, data analytics, it's another use case that is not fairly well understood in terms of the value it provides for HPC, but also the uniqueness that we can deliver through our data analytics platform called Rapids. And so Rapids is basically an open source tool that integrates with DAS and Spark 3.0, and it basically allows you to demonstrate your overall performance in data analytics. So we basically took a benchmark called Hpc XVB, and so that basically integrates a bunch of different workloads across SQL, ETL, machine learning, and NLP to basically show how you would get a full end-to-end big data analytics type workflow enabled across this benchmark. And what's interesting is just in a matter of months. So if you look at sort of, from V100 to A100, that's just getting your platform boost. But just through optimizing, the software, building in more optimizations around the communications across nodes, et cetera, we were able to, get a 2x improvement or 2.5x improvement, I should say, in just the overall TCO. So again, very, very compelling reasons to think about looking at these platforms. And then when we look at the energy efficiency, even though customers are using the cloud, what's starting to happen more and more, investors, regulatory bodies are starting to require companies to be accountable for their carbon footprint, even if they're consuming it via the cloud or via another company service. So the fact that our solution is 6 times more energy efficient than any other top 500 solution. For example, if you look at the top 500, GPU accelerated systems are 6 times more efficient. So in other words, while our average is right about 20 gigaflops per watt, the average right now is about 4 gigaflops per watt. So you can see that we have a significant advantage there, and it'll only get better as we continue to optimize throughout that step. And of course, it's across a number of applications. What makes this so powerful is that we've been at this for a long time, and it's not easy to basically bring all these applications on board, but we've really enjoyed the process and working very closely with developers, ISVs, partners, to really accelerate applications step by step. And then, again, it's not sort of a set and forget thing. You basically have to have some care and feeding to continue to get that benefit over time. But you can see it's across a number of different domains. There are over 1,800 GPU accelerated applications. We have roughly about 800 that are in our GPU catalog, it gives you a good glimpse of how customers are using these solutions across a number of different industries and a number of different scientific domains. So, I think we've talked about this and alluded to this in a couple of different ways, but again, describing the notion of the growth of data and really what's happening in scientific computing as a whole, and this is, both in terms of industrial use cases as well as scientific use cases, but there's a huge, shift in terms of leveraging AI as a tool. Because one of the great things I mentioned before is AI requires data. And guess what? HPC generates lots of data. So it takes a lot of that simulation data that you're using to simulate particle physics, that you're using to simulate quantum dynamics, etc. And it's training AI to understand those relationships. And so you have an example where we're like LIGO, where they were able to use, like I said, simulation data to train a CNN to recognize and identify gravitational waves in real time, right? So whereas before you would have to collect images, go back and analyze that data for hours, days, weeks, it was literally able to train a network and identify and sort of read through all the noise, whether it was, earthquakes, trucks rolling by. All of those things had very, very significant inputs on how the image capture process works. So being able to use AI to weed through all of that noise and instantly identify that was groundbreaking. In fact, I think there was a Nobel Prize in physics based on some of this work. Similarly, if you look at the work that was being done around, having faster predictions with ANI and MD chemistry. So basically in material science, you're trying to approximate and simulate particles, like, subatomic particles, and you're trying to understand not just how they interact with each other, but, the bonds and energy connectivities across those. And so this particular approach was able to use AI to estimate the energetics, but it was still able to use the approximation based on MD, which gives you a much longer time scale. So it gave you both worlds of quantum chemistry and molecular dynamics, and it basically sped up this overall process by 1000x. Again, orders of magnitude, not 5, 10, or 12, but 1000x. And so it's really revolutionizing material science, drug discovery, etc. So there's a number of these examples. So I won't go through all of them, but it's just really to drive home the point that this is truly transformational. Like when you're helping customers do this type of work, it not only changes, their work, but it truly changes the world. And there's no better example than, sort of a grand challenge that needs solving than COVID, right? And just drug discovery as a whole is something that has, I won't say plagued, but it has been a challenge for I would argue, most of life sciences, for years and decades now, right? So when you think about, what goes into creating a drug, I mean, literally it takes about 8 to 10 years and costs $2 billion. And by the way, 90% of those drugs fail, right? So you talk about having dynamics that are at play against you. Not only that, there's this phenomenon called Irom's law. And so that's the opposite of Moore's law. So it basically says it'll predict that the cost of developing a drug will double every 9 years. So again, there's a lot of incentive for life sciences and pharma companies to really get that virtual screening process down packed, so they can eliminate any wasted time, any wasted candidates in terms of identifying drugs. And so what's interesting, it truly is a full end-to-end workflow. It's not just one simulation. It's not just one type of app. It's not just one type of precision. It's across an entire mix of domains and applications. So whether it's looking at genomics or cryo-EM to understand the structure of the virus, or looking at data analytics to scour the universe of all the known compounds, right, to give you a good understanding of what's possible in terms of understanding unique drug candidates, or it's looking at document analysis and molecular dynamics to find the compounds that'll unlock the true nature of the virus. And you can see here, we're also using things like imaging for patient diagnosis, and even using AI and natural language processing to go through and scour, the thousands and thousands of medical documents that are created to look for correlations and cures and elements that they can highlight to help, speed the quest for a cure. And NVIDIA has been hard at work working with ISVs, working with developers, working with researchers to build solutions around these different parts of the workflow. And so you can see that we've had a lot of success. We have Clara Parabricks and CryoSpark, which accelerate the process of finding genes, finding the gene sequencings that allow you to understand the behavior and the genetic characteristics of its particular disease. We've built things like AlphaFold and Relion to help you understand that structure either from a physical standpoint or from a simulation standpoint. AlphaFold is using AI to predict the sequencing or the folding characteristics of the disease of the protein, I should say, based on the genome sequence. So it's taking another approach, but again, this is how scientists are using some of these tools. And again, I can go on, but the key thing is that all of these tools are being brought to bear to rapidly accelerate that drug screening process. In fact, just one of these things that's in the middle is this thing called the docking. It's a key element to understand, like I said, how a particular compound will fit with a protein and therefore unlock, the cure for that particular disease. And the thing is, we were able to do 2 billion compounds in a day. Like prior to this onslaught of research in this space, it would have taken years, literally, to do that same type of analysis. But by having all hands on deck, really leveraging the GPUs to its fullest, leveraging the Infiniband connectivity, leveraging all the other software that we bring to bear, we're able to kind of, accelerate that process dramatically. So I'll go ahead and wrap up here. I know it's late or earlier wherever you are, but hopefully you kind of take away some key things from the discussion tonight. First is that it truly is an end-to-end software solution. So when you think about NVIDIA and you think about what we're trying to bring to market, it's much more than a GPU, and we're working very closely with Microsoft to make sure that we're bringing fully sort of integrated end-to-end offerings. Also, when we look at the instances themselves, again, you have tremendous performance, tremendous choice, and tremendous scale. So you truly can rent a supercomputer for an hour. It's one of those things that I think is just blows your mind. You always hear those analogies about how our phones are more powerful than the computers that sent astronauts to the Mars. But when you think about how we can now literally rent and consume computing, it is truly incredible in how we're able to move that forward. And then last but not least, like I said, we're continuing to integrate across the ML, across the Microsoft Azure platform to make sure that, again, we're offering the best of both worlds, of giving you the flexibility of the cloud, but also giving you the innovation that we're delivering in the hardware and software. So I will go ahead and stop there. I'm a little over, but hopefully this is useful for you guys, and again, enjoy talking with you.
Dion and Dave, thank you so much. As always, just such a wonderful discussion, and I think I said this in the earlier session that I've spent a fair amount of time in the last 6 months with kind of more in the NVIDIA world than I've ever been, and it's just fascinating. It's really fun to be a part of. And like you said, at the end of the day, I think you guys have more software engineers than hardware engineers, and so when you start to when you start to realize what their focus is and where they're headed, it's mind-bending to a certain degree, but also very powerful stuff. So anyways, really appreciate that. So for the rest of the crew, we're going to finish up. I just have one kind of logistics slide I want to show here. We're going to wrap up for today. I want to thank everybody for attending day 2. We ask that you please complete our survey. The link is here on the screen. Just again, provide some quick comments. Shouldn't take more than, I want to say, like 30 seconds, worst case 1 minute. And then make sure you're registered for day 3. We're going to come back tomorrow. I know we spent a fair amount of time talking about products, roadmaps, kind of where strategically we're headed. Tomorrow kind of brings it back to the fold where, we're going to look at it from a partner perspective on teaching you guys how to scale deployments, back to a little bit to the sales cycle, a little bit to demand generation as we look at product marketing updates. And then Tim's going to kind of circle, our friend Tim Carroll's going to circle back around on industry updates after the break. And then we'll finish up with a partner showcase from our friends at Intel. So Please come back for day 3. I think it'll be great, and really appreciate everybody for making it through day 2 here. And if you got any questions, inquiries, or whatever, don't feel free to email us at hpcpartnerevents@microsoft.com. And with that, I think we're going to conclude day 2 here. I really appreciate it. So wherever you are in the world, have a wonderful day or night, and we'll see you guys tomorrow. Thank you. Bye.